Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
We are all looking for something. Some of us search for a treasure, some for inspiration, and some are looking for that which can only be found in our museum. Welcome to the Multimedia University of Kenya ICT Museum, the only one of its kind globally. Visit the main campus and be taken through the telecommunication evolution journey. For more information, visit our website at museum.mmu.ac.ke. MMU Museum, where the past meets the future.
Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, The Nobel laureate Abdus Salam believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society. From fundamental particles to black holes,
So I will first film. Yeah.
from climate change to quantum computing,
This lecture that I have.
work at ICTP is guided by curiosity and big ideas.
So this is maybe for half an hour.
ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community
Good morning. Today we start the first talk with Dr. Nikolai Kalini from Max Planck Institute of Science of Life from Germany. As I understood, he will continue with the last talk to conclude it, designing multi-core fiber for high-power fiber laser. After that, he will be covering another topic related to Kerr squeezing in fibers and subshot noise interferometry. Then the floor is yours.
Thank you, and good morning, everyone. So, indeed, I haven't finished 2 days before this topic about the fibers. So first, we'll talk a little bit about them, and then we'll continue onto a different topic, but still somehow connected to fibers, okay? I think I forgot to mention last time that even though I'm from Max Planck Institute for the Science of Light in Germany, the works that I will be talking about in this topic, I have not reached them yet, were done in the Institute of Applied Physics in Nizhny Novgorod, Russia, where I did my bachelor's and master's. Okay, so last time, that was the outline. We covered what the optical fibers are, the fiber modes, how to build a fiber laser, and about the self-focusing in fibers or in any media with third order nonlinearity. So today we will finish this talk by considering these two bullet points. Okay, so I'll just list through the slides, just as a reminder for you that the fibers work on the total internal reflection. And this is the structure of the fiber. This is how different fibers look like, the modes for the fiber. And then the fiber laser is just a simple loop of fiber. There are a lot of advantages, and as a reminder again, the constant wave laser, fiber lasers can reach quite high powers compared to the maximum powers that the constant wave lasers of different sources can reach. But the problem is with the pulsed lasers. With the pulsed lasers, we have via the Kerr effect, we have the self-focusing nonlinearity, which limits the peak power of a pulse in fibers to several megawatts. And this is very small compared to modern high-power pulsed lasers. State-of-the-art high-power pulsed lasers reach a power of petawatts, which is like 10 to the power of 9 larger than this limit value in fiber lasers. That's why, in this sense, the fiber lasers really don't reach that much of, don't reach the level of solid state or the level of bulk lasers in terms of peak power. And I said that there are a few possible solutions to this problem. One of them is coherent combining, when you have multiple sources of radiation, and after that you combine them together so that the total power of your final beam is n times larger than the power in each individual beam. And that's if, in principle, if you can go to a large number of these sources. This does not only apply to fiber lasers, but we will see how it applies to fiber lasers even better. Then you can, in principle, increase the peak power proportionally to the number of sources. And another idea is to design special fibers which support higher power inside of them. And we will start with this one, with special fibers. In principle, there are several types of these special fibers. You can go to hollow core fibers, where in the middle, where the most of the radiation is, you don't have medium. I mean, you don't have silica medium. That's why you don't see the self-focusing effect that much. And such type of fibers can really improve the high power support, but it's also not very easy to manufacture them. Because, I mean, the technology for silica fibers is very well known and very cheap, but for hollow core fibers, it's not that well studied yet. You can also just take a silica fiber and increase the fiber core many times to go to the so-called large mode area fibers, but then eventually, and I mean, people go through this limit a little bit, maybe less than 10 megawatts, but still higher than 1-2 megawatts with large mode area fibers. But in order to not fall into this trap of self-focusing, they have to keep the final section of their amplifier very straight in very stable condition, because every perturbation would still lead to self-focusing. So this is, even though possible, not a very practical solution. One way of avoiding this would be to go to multi-core fibers. So as you can see on the right here, a single mode fiber is just the core, a single core inside the cladding. So the core has the refraction index a little bit higher than the cladding. Well, when we talk about the multi-core fibers, it's rather obvious that this fiber has multiple cores inside of the same cladding. This could be as few as 2 cores, or as many as, in principle, hundreds or even thousands fibers. Well, what I've seen the most was 25 cores inside of a single fiber, and I will show you some works with these 25 cores. Now, in principle, each individual core can be single mode or multi-mode in this fiber. But I will only work with single mode cores in these fibers, meaning that each of these cores supports only one shape of the electric and magnetic fields. However, as we will see later, because there are many cores, there are some overall modes that cover all of these cores. So when you speak about the multi-core fibers, there are practically 2 types of these fibers. The first one would be so-called independent core, multi-core fiber, meaning that when the cores are far apart from each other, the field in one core doesn't see the other core. That means that the field in the cores propagate independently, and basically it's like having n fibers, n independent fibers, but close together in a single bundle. That, of course, has its pros and cons. Well, it's quite easy to do the power scaling then. You just launch the same power in each core, and you get the same amplification, for example, in each core. However, there are also some disadvantages. That if you want to combine the radiation from these cores, it's not that easy to do anymore, because every vibration, every thermal effect will give you different phase in each of these cores. And as, again, we will see a little bit later, having unstable phase between the cores is not beneficial for combining this radiation. You have to correct for that, and that is not always easy. On the other hand, and I mean, but still these multi-core fibers with independent cores are better than individual fibers in this aspect because they are in a single solid bundle, and these effects do not change the phase that fast as with individual fibers. Another approach would be to put the cores really close to each other. And because we know that the single mode of a single core is a little bit wider than the core itself, it will feel the neighboring core. And that's why the radiation in these cores would be entangled or coupled. Then, as we will see, if you launch some radiation inside of these multi-core fibers with coupled cores, then the phase in different cores would be locked together. And that's why we can easily or easierly combine the radiation at the output of the fiber. So we solve this problem of maintaining the phase, but there will be another problem, of course. And another problem would be that in principle we will have nonlinear effects, but on a larger and discrete scale. So now the self-focusing is still there, but now we don't have like an isotropic medium, but we have a few cores, and the self-focusing effect can be discrete, meaning that all of the energy would go into one core eventually. So is it possible to mitigate this effect? Well, first of all, we have to consider them. So I will only talk about the coupled core multi-core fibers, not about the independent ones. So in the coupled core multi-core fibers, the field inside can be approximated by the sum of fields of individual cores. Even though the cores are quite close to each other, they don't really affect the modes in each of the core, because the mode goes exponentially down when we are out of the core. That means that we can approximate the field by the sum of the fields for each individual core with some certain amplitude and phase in each core, okay? Then still, because this core, this exponential tail of the mode reaches another core, we have to add this contribution to the equation on the envelope of the fields propagating through the fiber. So if this Aith is the amplitude, the complex amplitude of the field in the ith mode, then its propagation along the z-axis would, additionally to the normal equation for fibers that you saw a few slides before, would have these linear terms. The first term would be the correction for the propagation constant in this core. Well, in principle, you can make the cores more or less identical, and then this delta beta would be 0, but in practice, it's very difficult to make the cores identical. Maybe some of them would be a little bit smaller, some of them a little bit larger, maybe also some skewed effect on them. So this delta beta, the change in the propagation constant from the ideal one, has to be included in the equation. And then the more important part is this one, which is basically, so this is the equation for the ith core, and it has linear terms with some factor of the complex amplitude for all the other cores. So all of the other cores contribute linearly to the complex amplitude of the ith core. And then that would mean that if we launch our pulse only in one core, it will eventually get spread to the other cores. And that is not very convenient to build the laser, because again, now the shape of the radiation is not predictable anymore. How to make it predictable? Well, you see that this is a linear equation. We can write it down as a matrix form like this, with matrix consisting of corrections and coupling coefficients. And then you know that if you have a linear equation like that, you can find the eigenmodes of this equation, of this matrix C, and then these eigenmodes, which we call the supermodes of a coupled core multi-core fibers, would propagate through the fiber without change in the complex amplitude in each of the cores. Then this matrix is n times n matrix, and you know that in n times n matrix there are n eigenvectors and eigenvalues. That means that in the multi-core fiber with n modes, there are exactly n supermodes. And you can see here the two examples that we will also see in the experiment. A single multi-core fiber with 6 cores arranged in a circle. It has 6 following modes that really resemble some modes in the normal multi-mode fiber. We have a mode where the phase and amplitude in each core is the same. That is the fundamental mode of this fiber. Then we have 2 modes with the single variation of the field around the cores. Then the 2 modes with 2 variations on the field around the cores. And the highest mode would be that the sign of the field in the neighboring modes differs by sign. I mean, in the first mode we have plus some value. In the next core, the phase of the field is shifted by pi. So it's vice versa. The electric field is directed in the opposite direction. And that we call the out of phase mode, because the neighboring cores are completely out of phase with each other. And this is the highest mode in this configuration. Now, for the fiber with 25 cores, so this is a square matrix of 5 by 5 cores. We have 25 modes. There are, I cannot fit them on the slide, but they resemble the modes of a rectangular waveguide. So the fundamental mode, again, would have all of the cores in phase, but the field in the cores on the outer bound of this matrix is rather small. The maximum is in the center, and then there is like a mode with a single variation and so on. And the highest mode, again, we call it the out of phase mode, would have the field with the pi shift between neighboring cores. So how is that useful? Well, first, before we go to how is that useful and why, I would say that the highest mode, the out of phase mode, would be beneficial for applications because it's not susceptible to, or at least not to that extent susceptible to the discrete self-focusing, and we will see why. But first, I want to talk a little bit about the experiment that we did some years ago to differentiate between and to find these modes in a multi-core fiber in experiment, to confirm that they exist and to find out some properties. And I think it would be beneficial to talk in detail about how this type of experiment looks like. So here on the left, you see the 25-core multi-core fiber on a microscope. Basically, you see the 25 cores inside, and this is the size of the cladding. So you imagine that if there was a single core, then it would look like a normal fiber, but now we have a little bit more cores. Then what we had here is the pulsed laser system, the Ytterbium fiber laser of 1030 nanometers. That was, well, you see the black line is the fiber, then it was collimated with a lens, and then it was put for to the face of the spatial light modulator. Now I will talk about that in a second. The light reflected from there was special filtered, as you know from yesterday's lecture, to get rid of higher order spatial effects, and then focused on the input phase of this MCF. Okay, so you see the picture from this input phase. It would be also a matrix synthesized on this spatial light modulator, which would resemble the highest mode that we want to synthesize inside of the MCF. Then at the output of the MCF, you see that the mode is filtered by the fiber because all of the higher spatial frequency modulations get out of the fiber because they are not supported by the fiber. And then an important part would be that the output of the fiber is transferred to the camera while simultaneously interfering it with a reference beam, with a plane phase, so to say. Why is that important? Because we want to distinguish the modes in this fiber. And we want to find out the phase in each core. So the camera cannot see the phase of the radiation, right? It can only see the intensity. So in order to see the phase and really find out which mode do we see, is it the in-phase fundamental mode, or is it the out-of-phase highest mode, or any in between, we have to interfere it with a reference beam and see some pattern like this, where you see the interference between the mode here and some reference beam. Now I will mention how to work with images like that and extract the phase information in a second. But before that, I want to say a few words about the SLM. So the SLM is a very nice device which in principle allows you to play with the front of your beam however you want. So imagine that you feel like a Gaussian beam, for example. In our example, it was a Gaussian beam. It has some shape of intensity and phase. Now, of course, you can change the phase using lenses, for example, or you can change the amplitude using like a knife edge or whatever, blocking parts of the beam or adding a neutral density filter. But what if you want to make something special out of this beam so that it does not resemble the Gaussian beam at all, or so that the number of zeros in this field is high? That is difficult to make with normal elements, normal optical elements. But there are these devices, spatial light modulator, which consists of many pixels. Like in this case, I think it was 800 by 400 pixels. And you can synthesize any phase mask in each of these pixels individually, so that the beam reflected from this surface at each point would get a specific phase, whatever you want. I mean, in addition to the phase that you had before, but if you know the phase that you had before this, you can synthesize any phase that you want. So how can we create a pattern like this at the input of the multi-core fiber? Well, there are different options, but what we did was basically, we know that the whole face of the SLM looks like this, and the beam that falls onto SLM has the size around this white circle. I think it should be visible. Then how to make a pattern like this and also alternate the phase between neighboring beams? Well, we synthesize a phase mask like this, where we have 25 squares with alternating phase in a pattern like this. So what you see is the phase mask applied to SLM. So this is the phase mask that gets added to the profile of the beam when it gets reflected of this surface. So these 25 squares with alternating phase would generate something similar to the mode that we want to launch in this fiber. And how to get rid of all the other parts of the beam, because it was a Gaussian shape initially. Well, it's rather easy. We create a very high frequency pattern on this SLM to make sure the reflected beam reflects in a different direction, not in the direction of the multi-core fiber. Well, namely, it gets directed a little bit off the axis so that on the diaphragm it gets deleted, basically. So this is like creating a grating on the SLM. And yeah, though these SLMs are very useful devices, and in principle, there are SLMs that not only support the phase mask, but also the amplitude mask in each point of the beam. So you can really synthesize any beam you want. Now, why? So in this setup, you can also see that in the reference beam, there is a delay line. Why is that? Well, of course, this interference pattern only appears when the time delay of the pulse that goes through the MCF and the time delay that goes through the reference beam is the same. But what is the time delay of the pulse that goes through the MCF? Well, actually it depends on which supermode is excited in this fiber. And in general, if you put some arbitrary radiation at the input phase of the MCF, you will excite all of the supermodes there. And all of these supermodes have different time delay. They have different group velocity. So by scanning the time delay of the reference beam and computing how much of an interference you have, you can find the modes that are excited in your fiber. That is also true for normal multimode fibers, but we use this method for the multicore fibers. So as you see here, there is a delay of femtoseconds from -2000 to 0, and there are 4 peaks with increasing amplitude. And these 4 peaks correspond to 4 different delays of the supermodes in this fiber. So the delay 0 would correspond to the out-of-phase mode, the highest mode, and the delay -2000 corresponds to the fundamental mode. Now, you may wonder why there are 4 peaks. We have 6 supermodes in this fiber. There should be 6 peaks. And the answer is, of course, that not all of the modes are really different. There are, for example, there is a pair of modes with a single variation of the field around the modes, and they have the same, they are degenerate. They have the same phase and phase velocity and group velocity. So we only see 1 peak for them. And the same is for the next pair of modes. So there are only 4 different group delays. Yeah, and this is, by the way, the 6-core MCF on the microscope that we used, but I think it's very difficult to see on the slide, the 6 cores in the center. I mentioned that I would talk about how to work with this type of pictures. Again, it's very hard to see on the slide, but on this pattern there is an interference pattern similar to what you can see here for 25 cores. This is for 6 cores. You see the interference pattern. Now, this interference pattern occurs between the reference beam and this out-of-phase supermode. How to extract the phase information from this interferometry? Well, if you consider the Fourier transform of this picture that is shown on the right here, you'll see a lot of noise, obviously, but this interference pattern will create 2 places, like two images in this Fourier transform field, because the interference pattern is basically a sine wave, and this sine wave creates a positive and negative frequency in the space. And then if you remove all of the intensity except for one of these spatial frequency, except a small circle around this peak, and make the reverse Fourier transform, you will get a picture like this. This is on the left is the intensity, and this on the right is the phase of the same picture. Now, because your reference beam only interferes with one of the modes at a time, you will get only a single mode out of that. So these 4 peaks corresponds to 4 pictures like this. We have the fundamental mode from experiment. So on the previous picture you saw, or on the 2 slides before when I explained the supermodes, you saw like theoretical pictures for the supermodes. Now the real supermodes look like this. The fundamental supermode with flat phase, the 2 degenerate modes with a single variation of the field. You can clearly see the zeros there, and the phase is flipped. Of course, it's not as flat as we want it to be, because the MCF is not as ideal as we want it to be, but still it's very close to what we want to find. Now with 2 zeros, and the out-of-phase supermodes with 6 zeros. And you can clearly see the radiation side, I mean the flip of the phase between neighboring cores. Okay? So the interference can expose the phase of your beam, and sometimes you want to look at it. Now we did the same for the 25-core MCF. And again, not all of the supermodes are present on the slide, but you can clearly see. So here on the top is always the experimental result, what we find using this interferometry technique. We have the out-of-phase highest supermode, like a with like a chess pattern in the phase. And this is the simulation result for the same fiber. We took the microscope image with all the changes in the radii of the cores and modeled the modes in this fiber. So you see the result is very similar. We have some, well, this is mode number 11, I guess, which looks that funny. But as you can see, it also corresponds to the simulation very well. And there is like a first, is it the first or the second? Of course, this is the second supermode with a single zero in between, and the fundamental supermode, which looks maybe not that similar in the simulation and experiment, but I mean, it's hard to account for all the perturbations in the fiber in the simulation, okay? What was also important in this work is that we wanted to launch in the MCF only the highest supermode, only the supermode like this. Because as you will see on the next slide, it is beneficial to have only this supermode to amplify it. But this supermode is not that ideal. It's not trivial to synthesize it at the input phase of the MCF, of the fiber. And if you just put some beam on the input phase of the MCF, you will excite all of the modes. And exciting all of the modes doesn't help you because you only want to excite this one. So how do we excite only this mode? Well, you saw this pattern on the SLM. Now you can modify the size of the squares and the phase in each of the square to try to find the correct position to only launch this supermode on the MCF. But there are 50 parameters for that. You have the amplitude and the phase for each mode. How do you find the only correct one? Or there are 49 actually independent variables. Well, you use the gradient descent method to try to adjust iteratively the phase and the amplitude in each mode to actually launch only this mode. And this turned out, and because you have the tool to analyze the content of the modes in the fiber with this interferometry and the delay stage, you can actually find out how much of the energy is launched into this supermode, and you can correct your algorithm for that. And that was very successful for both the 6-core fiber and the 25-core fiber. For example, in this case, 90% of the energy was in this mode after all the adjustments were done. And then basically only 10% of the energy is in different modes, and then we can already work with that. So sometimes you don't need a very complicated method of synthesizing the correct picture, or you don't need to understand the properties of this mode exactly. You can just use some adjustments and the feedback loop to find out the correct parameters. And that works in a high dimension space as well, like with 50 parameters. And I promised to tell you about why this out-of-phase mode is beneficial. Well, this is the result of a numerical modeling. We launch the mode that we found in the previous slide in the out-of-phase mode and the fundamental in-phase mode in this 25-core fiber. I think the fiber was scaled a little bit to allow for higher powers, but it doesn't matter that much. And we simulated the amplification of this mode. Of this, not of this mode, but of all the radiation in the fiber, like with complete 3D simulation. And as you can see, the in-phase mode, after some amplification, because of the self-focusing effect, all of the power goes into a single mode. And here at the peak power of a bit less than 3 megawatts, all of the radiation is practically in a single mode. And then a little bit more, and the self-focusing in this single mode would happen and will damage the fiber. But the out-of-phase mode, when we amplify even to 10 megawatts, which is 2 times the critical power of the self-focusing, you can see that because the phase of the radiation in the neighboring cores differs by pi, this self-focusing effect this discrete self-focusing effect is replaced by defocusing. And the cores at the corners, for example, get much more power than initially. And we hope that this would really help to build high-power lasers. And I mean, this works not only in the ideal situation, but also for some real-world super mode with, that we measured in experiment. So this is not symmetrical in any way. And you can clearly see the results here. So this is probably one of the possibilities to increase the peak power. The question would be, oh yeah, there is one more slide, but practically the same with the ytterbium dope. So this 6-core fiber was ytterbium doped to allow for amplification. And we did the amplification experiment. We did not reach quite the critical power. But as you can see here, the super mode, the highest order super mode remains the same after the amplification. So this, and the spectrum also. So this really gives us some hopes. Now you may wonder what to do with this 25 peak radiation. You want to have a nice Gaussian beam at the output of your laser system, right? To use it in the applications. And this also has to do with the first idea of how to increase the power of the lasers. That is the coherent beam combining. And that is a very broad topic. I would not go into many aspects of that. Just a quick note that the general idea of coherent beam combining would be that you have the seed laser that provides the radiation for your system. And now instead of having a single amplifier like in the master oscillator power amplifier scheme, you would have a splitter to split your radiation to several channels. This could be spatial splitter or time domain splitter or frequency splitter. There are different types of them. And then you will independently amplify each of these channels. And then after that, you will combine all of them again back in a single pulse. And this is, in principle, compatible with the CPA, chirped pulse amplification technique. So you can also have a stretcher before the splitter and the compressor after the combiner. This scheme is universal for different types of lasers and also for fiber lasers as well. For fiber lasers, you can have the seed laser and all of these elements, including the amplifier stages in the fiber. But as before, you have to combine them and to compress them out of the fiber, because otherwise, what's the point? You cannot combine high power inside of the fiber. You have to do that elsewhere in free space. Otherwise, you would damage the fiber. What are the practical schemes for this? Well, there are many of them. Can I have the slide going forward? But the most versatile approach, I would say, is the tiled aperture approach. And this is the theory behind that. And that has to do with the Fourier optics, as you learned yesterday. So on the left here, you have the field. So we arrange the emitters in a line or in a two-dimensional pattern on the left, and then let the light propagate a little bit until the fields almost touch each other, okay? Now, after that, we will install a lens array to correct for the spherical phase that each of these individual emitters acquires while expanding to this size, so that after this lens array, the phase of your beam is flat, okay? So we have the amplitude that looks like this, the red line, and the phase is flat. Now what happens if you let this beam to propagate into the far field? Or maybe you install the lens and look at the focal plane of the lens. Well, as you've learned yesterday, the result that you get is the Fourier transform of the initial field. And I mean, this picture is in 1D, but if you have a two-dimensional beam, you would have the same in each of the directions. And then what you get at the output would be one central peak and also some additional side peaks, because how is this? So the distance between the peaks would be defined by the distance between the neighboring peaks, the neighboring emitters in the near field, and the shape of each individual peak on the far field would be defined by the Fourier transform of the envelope of all of the beams. So S here, and this is the Fourier transform of S. And the shape of the envelope of the beams in the far field would instead be controlled by the individual shape of each emitter. Well, in this simple theory, we assume that all of the individual emitters have the same shape. Okay? And this is the technique that many people use now, at least in the lab, but also in some real high-power lasers. Well, you have if you only have a few emitters, this is not very productive. But if you have many emitters, this central peak can reach up to 70% efficiency. So the central peak contains about 70% of all the power in the initial beam. So imagine you have 20 emitters. Each of them would go up to critical power. Well, in the end, you wouldn't have 20 times the power, but you would have around 10 times the power, or maybe 12 times the power. This is already good enough. The thing is, with normal powers, with normal fibers, you have to really make sure the channels are in phase. And if the channels are not in phase, you wouldn't get this nice picture at the far field. And this is a picture of this work from Ramirez et al., where they used a fiber with 7 cores, but this was not a coupled core fiber. It was an independent core fiber. The near field at the output of the fiber looks like this, but then because it's an independent core fiber, the phase is not stable, and if you let it run without any phase stabilization, this is the far field that you get. Not very nice, right? But if you lock the phase of each individual channel to be equal, then you get this nice picture with a central lobe and some side lobes. And the central lobes contains about, I think in experiment it was about 50% of the power. So phase stabilization is crucial for this system, and papers show that you have to stabilize that up to 10 kilohertz. So the noise, the phase noise that you get can be up to 10 kilohertz in multi-core fibers with independent cores. And I mean, this phase stabilization technique is more or less mature. There are ways to do that very well, and people do that, but still it requires some additional setup. What we can do instead, well, before we go to what we can do instead, I wanted to show you what happens if the phase of individual emitters is in the out of phase mode. And this is a new result that we got a few years ago. So the picture on the left is the same as before, but now the phase in the neighboring emitters differs by pi. So it's out of phase. Well, you still have to do the Fourier transform to get the far field, but now instead of one central peak, you have 2 peaks, 2 central peaks. Because again, this looks like a sine wave. The thing is, if you now combine these 2 peaks somehow with a different method, like you can combine 2 peaks on a beam splitter with very high efficiency and very easily, then in these 2 peaks, almost all of the power is contained. Not 70% as before, but as our results show, 98% of the power is contained in these 2 central lobes. And adding a single beam splitter, I mean, you will have to correct to adjust the phase as well, but well, that is the cost of this approach. And in principle, you can get much higher efficiency. So this graph shows the efficiency of this approach on the horizontal scale is the distance between the individual emitters, and the efficiency is on the y scale. This blue line here is this. Well, it actually goes to almost 80% with the in-phase, with the standard approach. And this red lines is with this out-of-phase tiled aperture approach. So this is This could be very beneficial for applications. I haven't seen any paper that uses that for individual emitters yet, except for our paper. But why is this also beneficial for the case of multi-core fibers? Well, you saw that this field is what we get at the output of a multi-core fiber if you launch the out-of-phase mode there, which is stable to amplification, to self-focusing. And indeed, what we can do with this mode is just let it propagate to the far field, or again, focus it with a lens, and we get these two peaks at the output of the fiber. And we can combine them with a single beam splitter to have very nice single beam. So this is the result of the numerical modeling for this mode. Of course, in 2D, in this picture, you have not 2, but 4 peaks like this. And then you need 2 beam splitters to combine them. First fold it like that, and then fold it like that. So in the simulation, we get for this non-ideal mode 93% efficiency of combining with very high beam quality. M squared parameter is equal to 1.1 basically. And we also did an experiment with this 25 core fiber like this. So again, this fiber laser system, a terbium fiber laser system, the SLM-based launch system that we optimized for this out-of-phase super mode. Then at the output, we have these 4 lobes as expected. And then we had a somewhat complicated, but at the same time, much easier scheme to combine all of this into a single beam. And we did that with 73% efficiency. Well, not quite 100% as we hoped from the theory, but again, this is much higher than any efficiency you can get with the in-phase tiled aperture approach. In the in-phase, in theory, you can go to these numbers, but in practice, the numbers are much lower, like 40 or 50% in the experiment reported. So this is, as far as we know, the highest tiled aperture combining efficiency. And as you can see, the beam at the output is also quite nice. Yeah, I think that's all for this part, for the multi-core fibers and the coherent beam combining, and I will be happy to answer all of your questions.
So in terms of the photon statistics, these various schemes of combining, how do you think they compare? Because, I mean, ideally, if everything would be nice and fine, you can add 2 coherent beams and just get a coherent beam with square root of 2 higher amplitude without any additional noise. So is the combining with these different cores, is this maybe in terms of photon statistics the best route?
In terms of photon statistics, when we combine many cores, well, if you can only consider like 2 cores of them, I would say that the equation for the resulting field does not include any other like vacuum fields. So I think in principle this should be better than, no, I mean if you combine them on the beam splitter, you also don't include any other field. So this should be as efficient and as combining on a beam splitter. So there would be no additional noise, I would say, as far as I can tell right now. But of course, I mean, in the maybe it's not that easy to get the ideal photon statistics in the fiber, especially in this multi-core fiber with many inaccuracies. So, but maybe when this technology is mature enough, then yes. But you also can consider, like, this is just a transformation of a single mode of light, of a single, like, yeah, single mode of light, basically. So it doesn't really matter. There are photons in separate cores or the photons in the combined beam. The photon statistic should be the same if you take all of your light together. It should not change with these combining setups.
Okay, thank you. Yeah. So I was thinking, like, combine two coherent states, the uncertainties. If you combine two coherent states, the uncertainties are of course uncorrelated, but then they add, as a result, they add quadratically, and in the beam set has square root of 2 attenuation, and in each direction, so they add up to the same uncertainty, exactly the one that characterizes a coherent state. Yeah, I see what you mean.
Yeah, I think so.
Thank
I mean, you cannot change the photon statistic by changing the shape of the beam.
More question, please.
It's about this efficiency. If I just think about some power that I put in, and it's a nonlinear effect, but you are dividing in many fibers. So how does it work? Because it depends on the intensity per fiber.
Yes.
In terms of total energy efficiency you get.
So the total efficiency in our experiment was not high. I would say maybe 10% or something like that. Because a lot of the power is lost on the input interface. We did some, I would say, quite simple setup to launch the pulse in the fiber. But in principle, this fiber can be active, and it can amplify the signal. So for fiber, and maybe I will show this picture here. With the 6-core fiber that was doped, we actually did the amplification experiment. As you can see here, there is a pump of 975 nanometer entering the fiber as well, and all of the cores get amplified. So, and the output pulse is, I mean, orders of magnitude more powerful than the input pulse. So, in terms of fiber systems, the efficiency of the coupling is not that important. But in our experiments, it's also very low.
Okay, thanks.
Okay, thank you, Dr. for your presentation. My question is, you said it is impossible to make the cores identical when you are creating the multi-core fibers. Does it have any effect on the output?
Yeah, so, well, maybe I say a few words why it is difficult to make if the clicker works. So, okay, when you make the fiber, especially the multi-core fiber, what our colleagues did is to have some more or less thick rod, and then drill the holes there and insert the cores, and after that you melt this mold together, and then again in the melting process you extrude a thin fiber out of that. Okay, then and this is the source of these inaccuracies in the fiber cores, because when you melt your setup together, the cores on the in the corners and the cores in the center, they feel different forces from the melting process, and therefore the cores do not have the same size. And why does it not work? I wanted to show the picture, but I mean, you will have the presentation after that, and you will see that the cores are somewhat corrupted both in this fiber and in that fiber, in the 25-core fiber. Regarding how it affects the output, you can see on these pictures actually. You see that in the ideal case, all of 6 cores would have the same amplitude. But in our case, this mode that we see has much higher amplitude in 3 cores and much less intensive amplitude in the other 3 cores. So this is an example of one of the inaccuracies. And I mean, in this picture as well. And in this 25 core fiber, all of the modes should be symmetrical, at least the fundamental and the highest mode. But as well, you can see from the picture, it is not correct in our experiment. So that's how it affects the results. But also, we showed that it is not that important in the both in this high power stability and in the combining setups. So maybe, of course, the technologies would get better and better to make the multi-core fibers. Maybe we didn't have the best technology available at the time, but still you can already do some good results with that.
There is a question from the online.
Mm-hmm.
What are the advantages of using mult amplifiers in a CPC approach over using one amplifier?
So again, I mean, this doesn't work. Yeah, so CPA, chirped pulse amplification, was meant to decrease the high power, the peak power of the pulse in the amplifier, and then by stretching the pulse in time domain, and then bringing back together out of the medium. And this is compatible with coherent beam combining, because now this chirped pulse you can split into different sections and then amplify independently. What is the beneficial of CPA then, you would say, if I got the question correctly, because you already decrease the peak power? Well, CPA is much more developed technology, and you can do really fantastic things with that. And coherent beam combination is not that mature, and you cannot decrease the peak power 100 times, I would say. But with CPA, you could really stretch the pulse, I think, at least 1,000 times without any spectral aberration, so to say. So when you recombine it, it will be back together. So to make the same thing with coherent beam combining, you would have to have 1,000 amplifiers. And even though people think about that, especially in the concept of multi-core fibers, where you can really have thousands of cores, this is, at least for now, this is not practical. And I mean, it is always better to decrease the peak power 1 million times than only 1,000 times. So they work really well in combination.
Thank you, Karinin, for the presentation. Now, on slide number 27, where you have the lens array. Yes, I was thinking about the implementation of that scheme because I think the different beams that are getting to the lens array, I believe they have different wavefronts. So the lens array, probably unless we have adaptive optics, where each of the elements is going to behave in a manner as to focus the particular wavefront that is getting there. So I don't know whether you implemented this or?
We did a similar experiment using, again, a special light modulator as the lens array, because lens array manufacturing is not that easy. On one hand, well, on the other hand, there are manufacturers that do very quality lens arrays already, but we didn't have access to them. So we did that with an SLM array. And then if you have individual emitters and you have to correct for the phase front, and also, as you correctly said, for the wave front in general, if you have emitters not having the same position in this plane, you would have a different curvature, different wavefront curvature here, and in principle you have to correct for that. So an ideal setup would also adjust the positions of the individual emitters here to correct for this wavefront, because it's not easy to adjust the lens array unless you have the adaptive optics like SLM. So what we what we did, we corrected the wavefront on the SLM in the lens array. But in principle, it's possible to move, for example, the tips of the fibers so that all of the wavefronts are the same. And you can diagnose that by looking at the far field by, for example, turning off all of the emitters except one and measuring the focal spot. You should have the same focal spot for each of the individual emitters. And in this case, you would have, when all of them are turned on, you would have this nice picture. So this is a method of diagnosis. And also, for adjusting the phase of each individual emitters, you can do that by turning on two of them and making sure that you have the lobe, the interference lobe in this position and not somewhere else. This is how you make sure that they are in the correct phase. So these are some technical challenges, that's true. And we can diagnose that and we can adjust for them, but it's not very easy.
I've heard you talk about the amplifiers. So, and, I think that
I cannot hear you.
what I'm saying is, I've heard you talk about the amplifiers.
Mm-hmm.
And I think the amplifiers introduce or they degrade the signal-to-noise ratio. So if we have a series of amplifiers, and maybe one amplifier will introduce some noise to the signal, does it mean that the next amplifier will also amplify the noise which has been generated by the previous amplifier? Or maybe you can explain.
Yeah, I mean, this is true for the master amplifier, master oscillator power amplifier schemes, that if you have a series of amplifiers, then in principle any noise that you generate in the master oscillator or in the successive amplifiers would get amplified in the next amplifier and so on. And for noise here, I would say the main source would be ISE, so the amplifiers stimulated emission. And I mean, you have to be careful with that. That's what I can say. In fibers, so if you work with bulk optics, a lot of the noise, you can get rid of that by installing some special filters, for example. For example, this ISE does not always have the same direction as your signal, as your amplified radiation, the one that you can get. And therefore, by installing the spatial filter, you can make your beam cleaner and remove this additional noise. In fiber systems, it's not that easy because all of that gets propagated through the fiber. So you have to manage the pump as well to make sure there is not much noise added to the system.
My question is that due to optical Kerr effect in the fibers may cause nonlinear distortion in the signal propagating through the fiber. So how do you correct for those nonlinear distortion of the signals?
You mean the time domain distortions? Or okay. Well, for that, you are correct that I only talked about the spatial effects like self-focusing, but there are also time domain effects such as self-phase modulation, and it changes the spectrum shape, the spectral shape of the pulse. For that, I mean, for the fibers that we used, I would say the effect is not that visible. So So I would say two things. Well, I actually have them in this presentation, but I will say that now. That nonlinear effect self-phase modulation tends to collapse the pulse and broaden the spectrum. And that is usually beneficial for pulsed lasers because If you have a broader spectrum, you can have your pulse shorter. But on the other hand, so it is not always a bad effect on one hand. On the other hand, you also have the dispersion in the fiber that tends to broaden your pulse. So when they work together, it is possible, it is not that apparent because the dispersion cancels some of this effect. And in principle, it is also possible to launch solitons in this fiber. I will talk about that here. That compensate for this effect entirely. Yeah, and of course, if your spectrum gets very wide, then in the amplification stage, you only amplify part of it. And all of the parts that are not in the gain line width would get removed anyway. So this also limits this effect. But that's a nice question, yeah. Thank you.
Okay, if there are no more questions, we continue to the second part.
Yeah, indeed. The second part would be a little bit more difficult from the theory side, because I will talk about the Kerr squeezing in fibers and how to apply them to the shot noise, subshot noise interferometry. Well, yeah, this would be the outline. I would talk a little bit about light modes, but maybe we'll do that fast because you've already heard about that, as well as about the coherent and squeeze states. Then we will talk about what Kerr squeezing is. We'll go to polarization squeezing and Stokes parameters, which are essential parameters for polarization of the light. So this part will be mostly theory. Then again, I will go into the experiments that I did about the polarization squeezing generation in fibers, and then about the application of that to interferometers and about the Kerr squeezed interferometers that we made. So yeah, the classic modes of light, which are important for quantum applications as well, is when we have this wave equation in isotropic medium, you have certain solutions for that, and these solutions you would normally call the modes of the light. So the general solution would have oscillations at a certain frequency and some shape in the space. And for shape, there are different modes. The most fundamental one of them is the Gaussian mode that you can see pictured here and the profile here. I'm pretty sure you all know about this mode. There are, of course, some higher modes like this, shown in this picture. And when you talk about the mode of light, because everyone in quantum talks about modes of lights, usually single mode, you have to understand what people understand in what people mean by saying a mode. So a mode is basically a single solution of this wave equation. If I go to the next slide. So when we say a single mode, usually this is what we assume, that we fix for the light the propagation direction that I will talk about the Gaussian mode because it's the most fundamental one, but this principle you can apply to any kind of modes. You have to fix the waist position, so the focal spot of this mode, where you start counting your coordinates. You also have to fix the waist because light that diverges differently is different modes. And apart from these spatial parameters, when speaking about a single mode of light, you have to fix the polarization and the frequency of light, okay? So a single mode of light is some certain solution to the wave equation with a fixed spatial position, spatial direction, spatial size, with fixed polarization and fixed frequency, okay? Now, this is most general in isotropic medium. In fibers, for example, when we talk about the mode of light, you don't have many special modes as here. So you have the propagation direction is basically fixed, or you choose one of two of them, forward or backward. You don't have to choose any waist position in fiber because it doesn't change in size. You you don't choose the waste radius because there is only a single mode in single mode fibers, but you have to choose the polarization anyway out of 2 of them, or maybe some linear combination of them is also works. And you also have to fix the frequency. So this is what we mean when we say a mode of light, whether it's a classic mode of light or a quantum mode of light. And this mode of light has basically 2 properties, 2 real numbers that describe the radiation in this mode. That would be the intensity or amplitude. So the amplitude would be the square root of the intensity, and the phase. So the absolute phase in this mode. It doesn't really matter at which point you take the intensity of the phase. If you know the properties of your mode of light, and you know amplitude, or you know amplitude and phase in any point, you can compute the amplitude and phase in any other point. Okay? So this is important to understand, that these are the parameters of the modes, and these are what we can change staying in the same mode. Now I want to go to the quantum field. And in the quantum field, the field is quantized, and usually you come up with some operators for a single mode. And then you say that for each mode we have some operators. Now I won't go into any math of that to make this talk a little bit simpler. But yeah, what we really need is a quadrature space, or the phase space. And this phase space, this is still a classic picture. You have basically a 2-dimensional space, and a single mode of light is represented as a point in this space with a certain amplitude and a certain phase. Now, when you propagate this mode through different optical elements, you change the position of this point in this phase space. And because I removed the oscillations with the main frequency from the mode description, I would say that this, unless you have some optical elements, this point stays the same always for a single mode of light. Okay, so yeah, and also an important term for us would be the quadratures. So if on this polar plot you have the amplitude and the phase, then the Cartesian coordinates on the same plot would be called the quadratures of the light. And through my presentation, I would call them x1 and x2, but they are also sometimes called x and p. So what do we do when we go to the quantum domain? In the quantum domain, you know that there is Heisenberg uncertainty principle. That means that the conjugate variables can be precisely defined or measured at the same time. And that you probably know that in terms of position and momentum of the particle cannot be defined precisely at the same time. So you have to choose. What they really mean by that is that instead of having some certain position and a certain momentum, the particle should have some distribution of possible positions and the distribution of possible momentum. And when you measure the position or the momentum of a particle, you only get a sample from that distribution. And that applies to many variables, or all the variables in the quantum world, including the parameters of a single light mode. So on this picture, the same phase space as before, you have the quadrature variables x1 and x2. And the uncertainty principle tells us that you cannot define x1 and x2 for a single mode of light with precision at the same time. So you cannot no longer say that your mode of light is a point in this space. Instead, you have to say that there is a distribution. There is some uncertainty. And you have the minimal area for this uncertainty, limited by the Heisenberg principle. And this uncertainty is one of the sources of noise in experiment. Well, and we will, throughout this presentation, we will represent a single quantum mode of light as some uncertainty on this phase space, some shape in this phase space. Now I have to make a remark that not all of the quantum states can be represented as a blob of some uncertainty. Some of them have more complicated structure, but I won't talk about them. And yeah, as I said, this quantum uncertainty is one of the sources of noise in the experiment. So when you do an experiment, you don't always get precise results. You get some noise in addition to what you want to measure. And there could be different sources of this noise. In principle, you can split them maybe in 3 categories, at least when you do the optical experiments. The first one would be the detection noises. So that would be the noises not connected to any optical effect, like the noises in your detectors, amplifiers, and so on. That is usually called the technical noise. Now, the other source of noise would be the classic noise in your radiation. For example, you have a train passing by next to your optical lab, and you see these vibrations. Or your laser has some relaxation oscillations, and you have the amplitude of the radiation changes in time. So these are all classical noises. But even if you get rid of all of these noises, you wouldn't get exact results in your measurements because you have quantum noises. And these quantum noises are caused by this uncertainty here. And if you just look at this state here and try to measure its intensity, so install a power meter, for example, and look at its at what it shows, then basically what you get would be some number proportional to the number of photons in this mode. And the number of photons is the square of this distance, the square of amplitude, and each time slot that your detector measures this number of photons, you would get probably a different number according to the distribution along this line. And to give you the practical number, this distribution has such a size, or the smallest size of this distribution would be that the photon statistics, the variance in the photon statistics, so the number of photons you get in each time slot, is equal to the average number of photons you get in each slot. So the standard deviation would be the square root of the number of photons. And this is clearly seen on this. So yeah, one important thing to mention is that the quantum noise doesn't have any time scale. Every time you make the measurement, you get a different result from this distribution. And this is a very clear difference from the classical noise, because the classical noise usually have some time scales. And if you measure fast enough, you would get similar results, but it will drift. But in the quantum noise, however fast you measure, you would always get random noise within this distribution. So that's important. That's why you usually monitor the quantum noise and analyze it in the spectral domain. So here I have a picture of the real spectrum of noise that you get from an optical experiment, basically measuring the power of some laser. So this is frequency of noise in megahertz. This is from 0 to 20. Is it to 20? Yeah. And this is the noise power in dBms. So as you can see here, at smaller frequencies like here, you have very large noise. That is because of different technical noises, classical noises of the laser, and basically because at 0 frequency you should have the power of the laser. So 0 frequency noise is actually the average power. You also see some spike here around more than 18 megahertz, and this is evidently some classical noise, probably comes from the laser or things like that. But the quantum noise, because it does not doesn't have any time scale, in principle it should have a flat floor here. So it should be present at any frequency that you measure. we don't have a flat floor here. So, I mean, this is why this is clearly not a quantum noise. We don't have a flat floor here because this noise that we see is amplified with some different gain for different frequencies. But from some other measurements, I know that this line here is actually the quantum noise that I measure. So this distribution in the number of photons that you get with each measurement. As you can see, the frequencies are pretty high, and in principle, it can go faster, even for higher frequencies. And this is actually the limiting factor in some experiments that we will see later. So how to work with that? Well, I have to, I mean, you probably had this on Monday from Mojde as well. But I will remind you what are different quantum states that you can have for this single mode of light. Well, the thing that I showed you on one of the first slides was a symmetrical distribution, symmetrical uncertainty in this phase space. And this is called a coherent state. Because this is the best or the closest quantum description of a laser that you can get, of a noiseless laser. Because it has more or less defined amplitude and more or less defined phase. There are some other states as well. And this is usually, I mean, to work with noise in this state, usually people go to so-called squeeze states. So the squeeze states would, on this phase space, look like this, when you have not a symmetrical Gaussian distribution of possible outcomes of measurements, but rather an elongated distribution. And in this elongated distribution, you would have the minor axis. Along this like smallest size of the ellipse should be smaller than the diameter of this contour here. In this case, this state on the right is called a squeeze state. And we will see why and how it's important. So this squeeze state can be anywhere in this plane. And there are some special states which are important for applications. So some of the squeeze states are called amplitude squeeze states. And this is one example of that. As you can see, this minor axis is orthogonal to, or rather it's parallel to the vector that connects the origin to the center of the ellipse. What does that mean? Well, if you try to measure the power of such a mode or the number of photons there, you would measure the distance from the origin to some point here. But now, and I mean, the noise that you will see, the quantum noise, would be governed by the width of the distribution along this line. But now, this state is rotated in such a way that its minor axis is along this line. That's why if you measure noise from a state like this, or the fluctuations, then you would get a smaller level of noises than that of a coherent state. And I mean, that is obviously better for many applications because now you have less noisy results for all the frequencies at the same time. Then there is another squeeze state that's called phase squeeze states, which is orthogonal. I mean, the distribution is rotated 90 degrees from this one, like here. And as you can see, this state has a much better defined phase rather than amplitude. So if you make some experiment that measures the phase of this mode, you would get much less noise than that with a coherent state. Okay? Because now when you measure phase, you measure along like the polar angle here, and the distribution of the polar angle is now narrower than that of a coherent state. There are also some special states which are centered in the origin. I won't talk about them, but I think it's important that you know about them. If you take a coherent state, a symmetrical distribution, and place it to the origin, then that would be the lowest energy state that a light mode can have. And that state contains exactly 0 photons. That means if you measure it, If you don't have any other source of noise, you would get exactly 0 signal. Yeah, and as I said, this is the lowest state. This is called vacuum state or coherent vacuum state. Coherent because it has a circular shape. But in principle, you can also have a squeezed state, which is also located at the origin. And this is called a squeezed vacuum state. And well, one of the important properties is that it has strictly more than 0 photons. So in principle, if you detect this light, you have some power. You cannot say that it is amplitude or phase squeezed because it's difficult to define phase when the state is at the origin. But it is useful for some applications when you interfere it with a different light mode. Okay. Now, there is a slide on the Kerr effect. It's exactly the same as in the other presentation. So as a reminder, this is the third order nonlinearity in the medium. And basically, it's the change in the refractive index proportional to the intensity of the light field. We will see why it is important for the squeezing experiments. And this is the slide for the self-phase modulation that there was a question about. So now we go into fibers and we will try to see how to find the squeeze states in the fibers. And the effect of self-phase modulation will help us. So what is the self-phase modulation? The self-phase modulation is a nonlinear effect, the result of the Kerr effect, where the phase of the pulse, the phase of the radiation is changed proportional to the intensity of that radiation. So if you take a coherent, if you take a classic state of light that is represented as a point on this phase space, then the rotation around the change in phase, the change in polar angle, would be proportional to the intensity of the light. So the light with higher intensity gets more phase. Huh? Yeah? For the pointer, okay. Yeah. So, and in the nonlinear Schrödinger equation that is used for propagating the pulses inside of the fiber, you can see this clearly as the nonlinear term there. So the SPM is usually important when you look in the pulse effects, so the spectral broadening and so on, for the effects that there was question about. But it's also important, thank you, for the quantum effects, as we will see. Why is that important for the quantum effects? Well, if you now replace this phase space, this classical phase space, with a quantum phase space, then if you have a coherent state, because now the phase shift is proportional to the intensity, this coherent state would turn into a squeeze state. Well, this picture is a little bit exaggerated, but because usually these states are much, much smaller in comparison to the distance from the origin, but the effects look similar to that. Well, yeah, there is this Kerr-Hamiltonian that is useful if you want to describe that correctly in the quantum computations, but we don't really care about that. And well, this squeeze state will be useful for applications because it reduces the noises. Well, we will see how. And you can really generate a good squeezing out of fibers, because in fibers, even though the Kerr nonlinearity is not that high, it is much smaller than the second order nonlinearity in crystals, in typical crystals, for example. Because in fibers, you can confine the pulse in time and space for the whole length of the fiber, which can be tens of meters. You can have high effective nonlinearity, and therefore the effect is clearly seen. However, there are challenges in this approach. Because, well, first of all, there are different sources of noise in the fiber that will distort this picture. But also, this ellipse that you get, this uncertainty ellipse, you cannot use it directly to reduce the noise. Because if you now try to measure the noise along this line, so directly detect the Kerr squeeze state, you would not have the reduction in the noise. because as you can see, the amplitude is not squeezed. It is the same size as of the initial pulse. The squeezed is some combination of amplitude and phase, which is not that easy to detect. Now there is a slide that in fibers, I said you can confine the pulses in time, and that is precisely because of the combination of dispersion and cell-phase modulation. Dispersion tends to broaden your pulse, and cell-phase modulation tends to shrink your pulse in time domain. And in principle, if you have the proper size of this dispersion in the fiber, the negative dispersion or anomalous dispersion, then you can launch pulses into the fiber so that their shape won't change during the whole length of the fiber. And that will keep the intensity of the pulse, which will help you to produce high effective nonlinearity. Now, I said that it's not very easy to utilize these scarce squeeze states because they are not amplitude nor phase squeezed. How to work with them? Well, there are many approaches. One of them is to go into the polarization state. And to do that, we have to introduce some math. Well, you probably know about the Stokes parameters, which define the polarization of the light. There are 4 Stokes parameters. The first of them is basically the intensity of the light. And the 3 other parameters, S1, S2, and S3, define the differences in the intensity in orthogonal polarizations, like horizontal and vertical polarizations. And there is a minus there, in case it's difficult to see. So the S1 parameter is the difference between the power in the polarized horizontally and polarized vertically. S2 is the difference of power polarized diagonally and anti-diagonally. And S3 is the difference of power polarized right-handedly and left-handedly. And it is very convenient to show this polarization state in the Poincare space on the Poincare sphere, which would be a sphere with radius equal to S0, where the 3 Cartesian axes are S1, S2, and S3. And on this sphere here, you can clearly mark different important, you can point any polarization state of the light, but also all of the important ones are on the intersection of some axis and this sphere. For example, on the intersection of S1 in the positive direction, and the sphere is the light with horizontal polarization. On the opposite side is the vertical polarization. Now, if you look at the north pole, so to say, of this sphere, where the S3 axis intersects the sphere, then you have the right-handed polarization. And at the bottom, you have the left-handed polarization. So this Poincare sphere is a useful tool when you work with the polarizations of the light. If you want to work with that, you have to know how different polarization elements work in this space. And well, I won't stop for this slide, except that saying that different wave plates and different polarization elements, different birefringent elements actually implement rotations on this sphere. So if your state was originally circularly polarized and you install a quarter wave plate at a certain angle, like in this case parallel to S2, then you rotate this the whole sphere 90 degrees because it's a quarter wave plate, and 90 is a quarter of 360 degrees, and you get a state which is linearly polarized, in this case horizontally. And all of the wave plates that you can in principle make are represented as some rotation on this sphere. So this is really a useful tool to look at the polarizations of the light. Now, why do we want to go to the polarization squeezing? Well, that's because if you consider, well, this I'm going ahead of myself. So first of all, of course, you can define the quantum Stokes parameters, which are analogous to classical ones. Again, I won't go into the math. And then it is a convenient, they are convenient variables because with polarization optics you can measure any linear combination of the Stokes parameters. On one hand, and on the other hand, you also have the uncertainty relation between the Stokes parameters. Well, it looks somewhat complicated, but if you look at this Poincare sphere, basically your state must have some uncertainty that is not smaller than some certain value. So again, the coherent state on this sphere would look like a circular distribution, and the squeeze state on this sphere would look like an elliptical Gaussian distribution on this picture. And because we can measure any combination of the Stokes parameters, it's quite easy to determine if the state of light that you have, well, now it has two modes. It's not a single mode, it's a two-mode state. For example, a horizontal and vertical polarizations. We can check if this state is squeezed or not, and how much it is squeezed. And maybe we can also make use of it. So why did we go in this direction? Well, because the Kerr-squeezed ellipse is tilted, and there is no reduction in the photon statistics. But if we combine two such states in the orthogonal polarizations, which you can do with a polarization maintaining fiber, if you launch a pulse into a polarization maintaining fiber, as you will see, you get one Kerr-squeezed state in one axis of the fiber, and the other Kerr-squeezed state in the other axis of the fiber. Now, if you look at the beam as a whole, this beam would be polarization squeezed, meaning that some combination of the Stokes parameters would have smaller fluctuations than the same combination or any other combination for a coherent state. And if we set up our experiment in a way that we only measure this combination, then we would get more precise results. So I think I won't go into the details of the experiment, but basically, as you can see, there was an older experiment of 15 years ago in Max Planck Institute for the Science of Light, where they launched pulses into a polarization maintaining fiber. Now, a polarization maintaining fiber is basically the same single mode fiber as we discussed before, but it has some additional stress elements so that it is birefringent. And now there are fast polarization axis and the slow polarization axis, as with any birefringent material. And if you launch a pulse polarized along one of the axes, it would always stay with the same polarization. So it's a very stable system. So what they did in the experiment, they launched two pulses, one polarized along the fast axis and one along the slow axis of the fiber. There is some birefringence compensator to make sure that at the output of the fiber, these two pulses come out of the fiber at the same time. Now, with the help of some polarization optics, namely a half-wave plate and a Wollaston prism, which is a kind of a polarization beam splitter, so it splits horizontal and vertical polarization into two beams here. They looked at the fluctuations of this combination of the Stokes parameters, which is reduced in comparison to the coherent state. And they reached quite good results of the reduction of fluctuations by 6.8 dB. So dB is a logarithmic scale. This corresponds more or less to the reduction of the noises about 6 times, I would say, or 7 times in comparison with the original one. And what I did for my PhD work, yeah, this I think I will skip, is first of all a new version of this experiment which gets rid of the birefringent compensator in the front of the fiber. Instead, I splice two pieces of the same fiber, but in the second half I rotated 90 degrees, so that if I launch some pulse with with parts polarized along the fast axis on the fiber and the slow axis of the fiber. Of course, because of the birefringence and different group velocities, the velocity of these two pulses would be different. And at the middle of the fiber, there would be some delay between these two pulses. But because the second part of the fiber is rotated 90 degrees in respect to the original part, then the velocities would be swapped in the second half of the fiber, and the pulse would be, both parts of the pulse would be together at the end of the fiber again. And therefore, we don't need a birefringent compensator in front of the fiber to match the group delays of the two pulses. And we also don't need the phase stabilization system. Because in order to measure squeezing, you have to make sure that the phase between the two orthogonally polarized pulses is fixed. And for that, before, 15 years ago, they used a special feedback loop to compensate for all the possible drifts. But now, because I have a solid fiber, and both of my beams propagate through the same spatial mode at all of the times, I don't need it anymore. And yeah, this was a very successful experiment. I could measure the reduction of the fluctuations of Stokes parameters with some polarization optics, basically. The best squeezing that I get was a little bit higher than before, more than 7 dB of squeezing. Again, I think I won't go into details of this experiment. This is some level of noises for the shot noise, which basically is the noise of the coherent state measured over time, and the noise of the fluctuations of the squeeze Stokes parameters, which is some few dB lower than the shot noise for the duration of 100 seconds without any adjustments. So this is a very robust system that can find some applications in the future. Now, yeah, this is a fiber, the polarization maintaining fiber that we used. As you can see, there is a core in the center, but there are also some stress elements to make sure it's polarization maintaining. And this is the setup that we used in the MPL, but I think the quality of the screen does not allow us to talk about the individual elements. There are some results. As you can see, the best squeezing that we can get is below 7 dB, but I won't go into details right now, because I want to talk about how this is useful. And well, one of the earliest possible theoretical applications of squeezed light, so the light with some quantum variable having less fluctuations than that of a coherent state, was to use them in interferometry. Why is that important? Well, you can see a general interferometer on the top here. It has 2 inputs and 2 outputs. And the goal of the interferometer is to measure this phase phi that is introduced in one of the arms of the interferometer. So how precise this interferometer can be? Well, basically, this interferometer is in any detector that detector that you can use. Well, you launch some light from the left, and you measure some parameter of the light that exits the interferometer. Let this parameter be P. So now you have some dependence of the parameter P that you measure on the phase phi, which is introduced in the interferometer. The smallest change of phi that you can measure, at least from the experimental point of view, would be such a change so that P that you get, the parameter P, which could be, for example, the power in one of the output ports, or the difference in the powers in the 2 output ports, or whatever. When this change in P is larger than the fluctuations or the variance, the square root of variance of the P for a single parameter phi, okay? Because if there is some fluctuation, some error in P, and you change phi a little bit so that the next value is within this fluctuation, then you cannot distinguish these 2 values of phi. And that defines the precision that you can get. And it was proved long ago that when you only use the coherent states of light, the best precision that you can get is proportional to 1 over square root of n, where n is the total number of photons or the mean number of photons for the duration that you measure that passed through this interferometer, both from this and this port. However, with quantum states of light, you can actually do better, and you can go as far as 1 over n. And this is much better for applications, because with the same power of the light, with the same resource, you can increase your precision, in the orders of magnitude, few orders of magnitude. Why is that important? Well, in real life applications, maybe the quantum noise is not that high. But there are, the GIF doesn't work, okay. There is this important experiment in physics, the detection of gravitational waves. So the gravitational waves are waves that change, that shrink and elongate the space in orthogonal directions, and scientists wanted to directly measure these gravitational waves for a long time, for a century basically. There are different sources of the gravitational waves. I won't talk about them, but usually it's like merging of two black holes far away in our universe. And the power of the gravitational waves, or the amplitude, is measured by strain, which is the relative change in the distance that we see. And this strain can be, or that you can find in the gravitational waves that reach Earth, are as small as 10 to the power of minus 21. So that's, I don't even know the word for that. And even if you look at the long distance, like 4 kilometers, then the change in the distance would be 10 to the power of minus 18 meters, which is very small. So you want to have a very high precision interferometer that can measure that. And this is the LIGO interferometers, which, as you can see on the right, it's a huge 4 kilometer long observatory with a principal scheme like that, which can detect these small changes in the distance. And they use really huge powers of light to detect these changes. And this is where now the squeezing experiments are used as a tool to push this sensitivity beyond what you can do with the classical light. And the second part of my PhD, I would shortly talk about that, was to implement a similar change, a similar improvement in the sensitivity of an interferometer that you can get with the Kerr squeezing. So what I showed here in the LIGO, they used a different type of squeezing, the squeezed vacuum state that I showed in one of the first slides, to push the sensitivity beyond the shot noise limit. What we wanted to do is to do the same thing, but with Kerr squeezing. And the Kerr squeezing is tilted, as you remember, so that there is no amplitude and no phase reduction. So it is not directly applicable to our interferometry. So I think, again, I will skip this slide. And I will only say the takeaway from this experiment. And the takeaway is that in order to utilize the squeezed light, you have to make sure that whatever parameter squeezed, in this case, this axis, has to coincide with the variable that you want to measure. In this case, the phase shift psi. This phase shift psi should move this state along its minor axis. And you also want to detect the same parameter along which it is measured to get the highest sensitivity possible. And in case of Kerr squeezing, it is possible to do so by first generating a polarization squeezed light, as I explained, in the fiber with two modes, then combining them together and doing a base change to align the uncertainty ellipse that was initially tilted properly with the axis of our setup. And then in the second interferometer that we call the sensor, now we can detect this phase psi with better precision than before. So this was the experimental setup you generate in the, maybe it's better to show in this picture. This was the experimental setup, the laser fiber, no, it was not the fiber laser, but then this fiber with the 90-degree rotation in the second half that generates the squeeze state. Then the rotation of the ellipse we fix with this half-wave plate, because in the Stokes space, you can do basically every change to your state using polarization optics, such as wave plates, and in this case, one wave plate was enough. And then the sensor, we are yet to implement a full-scale interferometer, but we used a polarization interferometer with stress-induced Bielefeld regions to generate a signal. And there on the right, you can see, so this is again the frequency, and we generate a signal at 1.3 megahertz. You see the high signal at the output of the interferometer. And then we measured the signal using coherent light, so that without the fiber, without the squeezer, and it has this noise floor, this quantum noise floor. And with the squeezer, you can see that the signal is the same, and the noise floor is not that high. So we improved the signal-to-noise ratio by a few dB, which was very nice. So yeah, I think that's all for me, and I will be happy to answer any questions.
I read some questions.
How do you determine short noise?
So there are different methods to determine the short noise. What we used is to look at the difference channel. So we have a balanced detectors. We split the light of the same power into two parts, and then we take the difference channel from these two detectors, because then you measure the vacuum fluctuations that enter the vacuum port of the beam splitter, and we also verified that it is the quantum noise by looking at the scaling of the power of the noise.
If there are not more questions, let's thank the speaker again.
Thank you.
We have last moment information. Yes, we update. We had some issue with the speaker at 12:30, 1:30. He cannot present today. Then we have to shift his conference. And in the meantime, okay, we have a conference after at 12:30. We'll go to the experimental session. 12:30, 1:30, and then we'll come back for lunch, and then we'll go to the experimental session. And now we have the coffee break. Thank you.
Wanaangalia time. Sisi tunaenda na time. Leo hatujachelewa.
There is a question here.
No problem.
Eh?
You can call him to answer.
Yes.
Yeah. Mwambie ajibu.
Kumbe tunaonekana smart hivi tukiwa on.
Hey. Hi, I'm Acheng Brittany. I'm a final year fourth year student in Multimedia University. I'm attending the East African Summer School. It's a period of 2 weeks from 5th to 17th of May. So far, we are at the third day. It's been insightful. We are networking. We have talks like from people from all over the country, from Italy. We've met people from Germany, people from the Max Planck Institute research group. Yeah, and so far we've learned so much, and hoping by the end of the period we'll have learned and obtained a lot of knowledge.
Yeah, my name is Hilaria Radi from the University of Kabianga, currently pursuing an MSc in Physics, Optical Fiber Technology option. And I'm just thrilled to be here at the MMU University, courtesy of our school attendance. I'm here to attend the East African Summer School of Optics and Lasers. And so far the interaction has been very productive. I've been able to interact with scholars from various institutions, whereby I've been able to learn a lot from them. And I'm just thankful for this opportunity. I'm thankful for the hosts, that is the MMU, together with the partners ICTP and the NEO Lab, for the opportunity, and I'm looking forward to a more positive interaction, to a more intrusive and more interactive session with every scholar and even the organizers of the program. And definitely we are going to move on together as scientists, and we're going to move together as a unit, all in pursuit of academic excellence.
Hi, my name is Jabet Raquel. I just finished my Bachelor of Science in Applied Optics and Lasers. I'm currently a participant in the East Africa Summer School for Optics and Lasers, and this is currently the third day. I am enjoying the lectures from various doctors and professors. I really like how it's diving more into female speakers, which is giving us the motivation to venture into the optics and laser field. This summer school program has really helped me in gaining a better understanding, and I really enjoy and looking forward to what they have in store for us.
My name is Megana Maura Simon. I'm a fourth year student at Multimedia University of Kenya. I've come at Multimedia University of Kenya to attend a East African Summer School for Optics and Lasers through the International Conference for Theoretical Physics, and I'm very pleased to interact with different people from different diverse of this world, from different countries such as Italy, we have Belgium, we have Netherlands, and it's been an interactive session to interact with them for their research works they are doing, and they are very open to teach us and interact with us also, and they are ready to show us ways that they have done, the works they have done, and expose us to the various technologies that are outside there. We are very pleased, and I'm happy, and I hope to learn more as we continue in this East African Summer School for Optics and Lasers.
Wow, thank you so much. I'm David Kaile, and I'm from Multimedia University. I'm an MSc student, in other words, a Masters of Science in Laser Technology, and that has been our wholesome experience to gather a lot of information concerning optics and lasers in the Easter Summer School Conference. And I can tell you it has been a wonderful one. In fact, we are still waiting for more. By the end of this conference, I'm targeting to have gathered a lot of information concerning my field and also what I aspire to have in the nearest future. Remember, doing Masters of Science in Laser Technology, I'm also aspiring to have my doctorate in a field of photonics, and how I wish to gather a lot of knowledge from the resourceful people who have just come in, including also the president of Optica. That one is amazing. Thank you so much. I hope you are still enjoying also wherever place you are. Just follow us online at Multimedia University in the YouTube channel. Thank you so much.
If I change the wavelength, then also it's gonna move. So if I put white light, I'll see little rainbows, because every order will have the light at every wavelength a different angle. So this grating 1. Let's see grating 2. So the grating next is 2. So what happened now? What do you see now? They are getting smaller angles. So now you can think in the diffraction way, well, if I have a smaller angle, is the grating period larger or smaller than the first one? So I don't see. You think about it at home, but you see still the same thing. Yeah. But what this tells you that, okay, if I want to have an array of spots, I can make this array of spots very easily. I just put a grating. So I don't need to take a laser and divide it in beam splitters or split the light. How you split the light in many spots. So this is, a grating does that. Okay? But that's is like a linear thing, yeah? Because it's a grating is like this. So let's see, this is the next one is the chessboard. Well, what do you see now? Now you are away from the line. Now you see everywhere. Yeah, you see in 2D those spots. But you see that they are not like, they are here also, but these are less bright than this one. Okay, so let's see what happened. So I change the period. See, this is the new one. So I only change the period. So the plates, the same plates. So you see that now they are more squeezed. Yeah? So you can think about, okay, if I start mixing things, putting slits, putting squares, maybe I can make anything. Yeah? Maybe I can make anything. Because I can calculate, okay, what do I want here? And I calculate what do I need here via those Fourier transform relations. And so that's what we are going to see. And let me see which ones. So here is a whole element. So the PF1, PF2, PF6, PF5, PF3, and PF4. So you all write down, or if you don't have a pen, I don't know, do you have a pen? You can write down what you see, okay? So let's go to PF2. PF2. Can everybody see? What do you see? What is your PF2? So you see a square, but each square there are points, right? So there are points. So I can count how many? 1, 2, 3, 4, 5, 8. 8 points. So 8 by 8. So it's a 64. It's like a chessboard. 64 beans. So I made with this little plate 64 beans. Yeah. So it is called the diffraction optic elements. So what you see here, of course, there is a lot more here. These are, again, this is the second order of this whole thing. It's the same thing as the grating. You have the first order, second order. So you see this also repeating. We're repeating everywhere. So you see the repeats in many places. Every time a little bit less bright. But maybe sometimes you are only interested in the center one. And you see also this bright spot in the middle. That is the non-diffracted one. So it's the beam that just goes through. Yeah? What's the next one? 6. PF6 is this one. What do you see? You know this? It's the flag of the European Union. Yeah, you see all the stars. Wow, the flag was just like a vertical, should be horizontal, but I just put the plate like this. But you see that you can make stars, and you can make the frame. This little phantom you see is probably because of a double reflection, but you don't care about that. But you see, you can make, so you can say what you see, PF6, write down, make a drawing. The next is PS5. PF5. Well, these are a bit difficult to see. It's you see, it's written like Nemo, and there is some like ellipse. There are stars. So NEMO is network of micro-optics. It's the logo of the network of micro-optics. So you can do your logo with light. So this has to show that you basically can make anything you want. Yeah? You just have to calculate it correctly. And again, you see those repetition of this everywhere else. Of course, this takes a lot of energy of the laser to see one, so you don't see many. You see one here and a little bit here also. But because it spreads a lot, it spreads a lot the light. And again, the zero order is still there, right? Okay, so we go now to PF3. Maybe you can quickly see what PF4 is. See, this is like, again, a figure. And now we go to PF3. Now this is a very important factor. It doesn't seem to be very spectacular, but it's very important. What do you see there? You see what is called a top hat beam. You know, a top hat beam is used in microscopy. It means that the intensity is flat and then abruptly goes to zero. So it's round, so the intensity here is all 1 and then goes to 0. So that's interesting because in many lasers are not like that. Yeah, so although it looks like when you see the beam is actually like this. Right? It's a Gaussian. But a Gaussian means that you don't have a constant intensity everywhere you are illuminating. So if you want to illuminate with a constant intensity object, you have to, usually you make a very big Gaussian, yeah, so you make the beam very big, and then you only use a little part of the beam because there you can say, okay, this intensity here is constant. So you lose a lot of energy because you're spreading the beam just to take a little piece because you want this being constant. So if you need the beam being constant, you want to make a top hat beam. And what do you think this, except for microscopy, where would you like to have such a beam? For drilling holes. Think about it. Laser, you can drill holes in materials. But if you have a Gaussian beam, you're not going to make a very nice hole because the center will be more than the other. So the hole is not going to be very sharp walls.
Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
We are all looking for something. Some of us search for a treasure, some for inspiration, and some are looking for that which can only be found in our museum. Welcome to the Multimedia University of Kenya ICT Museum, the only one of its kind globally. Visit the main campus and be taken through the telecommunication evolution journey. For more information, visit our website at museum.mmu.ac.ke. MMU Museum, where the past meets the future.
Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
to Multimedia University of Kenya, a center of excellence in engineering, ICT, and business studies. This is the iMac Lab that offers editing skills and use of iMac computers with various video editing softwares such as Final Cut and many more. This is our engineering lab, where we conduct technical evaluation of hardware equipment and software troubleshooting and fixing every possible technical issues. This is our physics and chemistry lab, where most practicals happen, including tests on materials and present research findings to scientists, ensuring safety and quality standards are met. This is our laser and optics lab, which deals with laser and optics, including transmitting and manipulating laser beams or any other forms of laser light. Welcome to our radio. We have our own radio station that provides information to the citizens and people at Gatarongai. Listen to the sweetness of our radio on 99.9 FM and learn more from our students as they bring to you hot shows. This radio has greatly helped students acquire communication skills in readiness to join national and international radio stations.
So good morning. we can settle down. So thank you. So I will introduce the next speaker. Our next speaker is none other than Professor Geoffrey Kihara Rurimo. And because he has done a lot of introduction of other speakers, I take this chance now to also introduce him so that you can know more about Professor Rurimo. So Professor Rurimo studied his BSc degree in physics at Jomo Kenyatta University of Agriculture and Technology. He graduated with a first-class honors, then proceeded to University of Adelaide in Australia for his master's in optics. Later, I think now we all know that he did his PhD in optics and lasers at the Max Planck Institute of Science of Light. So currently, Professor Rurimo is the acting Deputy Vice Chancellor in charge of Administration, Finance and Planning. He'll come and give a presentation on the overview of research at the National Institute of Optics and Lasers. So with a clap, kindly let's welcome Professor Kihara.
Good morning, everyone. Today we are going to present to you an overview of the research that we are doing at the National Institute for Optics and Lasers. And this research is based on some work that we have done before, which is on high numerical aperture focusing, where we focus beam strongly, but these beams, we have them specially prepared, and we are going to present how we are going about that, preparing higher order modes, in this case the radially polarized beam and the azimuthally polarized beam. The purpose of that research is to focus those beams and study the electric field distribution in the focal region. And we intend to use graphene structures for that purpose, to study the focal region of the highly focused beams. So we are going to make that presentation. Now we are also going to have a presentation to do with the spectroscopy, some study we are doing on spectroscopy, which is a major research. And our presentation this morning, we are going to have it differently because we are going to have 4 students, master students who are undertaking this project. They are going to give us the work they are doing, which is a reflection of the research that we are having at the National Institute for Optics and Lasers. Now, the first student who is going to make the presentation is Sandra Achieng. Sandra Achieng. Sandra Achieng is going to tell us about how she's producing these higher order modes. Interestingly, yesterday she got the first prize for poster. But then I was not involved, so I was not a judge in that one. So I don't know how they did it. So, and we are using very cheap material to help us build a spatial filter, and that is cellophane sheet. And she's also going to tell us that it is not easy really to get that good cellophane sheet, which actually behaves like a half-wave plate. And in this case, she was lucky. After trying many times, she was able to get a cellophane sheet which actually behaves like a purpose-built half-wave plate in the visible range, all the way from 400 nanometers to 780 nanometers. I mean, sometimes you get a sheet that is good from 500 onwards to about 800. Sometimes you get one which is good in the lower wavelengths, but she was able to get one that actually works quite well in the visible region. Now, from Sandra, we are going to have Sylvester Kemonyi. Now, Kemonyi is doing some theoretical simulation on graphene. What happens when we illuminate graphene with different wavelengths and also different polarization states. So here are some results that he's also going to present. Number 3, we are going to have Christabel Asagi. This one is doing experimental, illuminating graphene samples using the different polarization states. We are to the point where we are focusing. First, we decided to understand the structure first. Using the normal illumination with beams that are not focused before we get now to the highly focused beams. And the last one, we are going to have Dorothy Koki, who is going to talk about quite some interesting work that we are doing on spectroscopy. So I would like us to welcome Sandra Achieng to come and make her presentation. 15 minutes as agreed. 15 minutes.
Hello. Okay. So I'll be speaking on a wideband cellophane-based polarization converter for the production of the higher order modes, which are the donut beams, TEM10 and TEM01. Light beams have polarization states which are reliant on the electric field of the beam of light. Therefore, it's possible to get light with various polarization states, which can be linear, radial, circular, all that, based on how the electric field is oscillating. In this case, we are seeking to produce the azimuthal and the radially polarized beams. I have followed various research works, which were such as the ones listed there. Some proved that cellophane could be birefringent, while others created polarization masks with various materials. In such a case, you find that it was possible to create polarization masks with diffraction plates, with some cellophane, but with a few segments, with the microfabricated spiral face plates, and even the liquid crystal masks. Following the lack of a wideband cellophane-based polarization converter for the production of the higher order modes, the TEM01 and the TEM10 beams, we focused on doing that to be able to produce them for the entire visible spectrum and to also ensure that they are very efficient, like they are of very high quality as compared to what has been done before. So that is what is in my problem statement and justification. The first step was to determine cellophane birefringence. It was necessary to find cellophane samples. Cellophane, it's a bioplastic material. It's transparent, very thin. It's like the paper used to wrap flowers and the one used to like cling film, the one you use in your kitchens. So we tried to find the fast and the slow axis for the samples, and then we tested them over various wavelengths. These are the lasers we used: 632 nanometers, 780 nanometers, 420, and 532. This is the setup for the 632 nanometer laser. This is the schematic for the setup used. And this is the setup for the 532 nanometer, the 420, this is still 632. 780 was almost transparent, so you could hardly see the beam. These are the results we were able to attain, whereby we compared cellophane material to a birefringent material, which is the half-wave plate that we use in the labs. It's made of birefringent materials. We used the half-wave plate, which was the blue graph, and then 2 samples of cellophane, which then allowed us to see these results. We did it over various wavelengths, 532, 780. The 4820, you had like, this sample wasn't good, but we found another one. We realized that it wasn't actually affecting the properties of the material. Therefore, we realized it was possible to do it with other samples, and we were able to find a sample later which could do the same. When we did this, we needed to find the modulation of the sample, the maximum versus the minimum, to see how much difference we had the modulation to be able to find the contrast. For the sample 1, we see it's 0.96. For sample 2, it was 0.86, while for the half-wave plate, which was the ideal in this case, it was 0.99. Therefore, cellophane can be used as a half-wave plate as it is birefringent. After coming up with this, we then fabricated the polarization mask. To do this, it was necessary to align the sheets correctly. We came up with this schematic, which was based on what was done with the liquid crystal plates from the paper listed down there, Machiavelli et al. 2007. Then we used a CNC laser engraving machine. We cut the machine in the cellophane segments. We did a 4 and an 8 segment mask. This is when we were doing that. These are the dimensions of my mask, as we tried to find one that would fit in with the other optical elements. Then this is one of the segments as I tested the birefringence for the sample and to test that I had cut it correctly. So as you can see in the diagram, the first axis is at the 22.5 degrees. So we did that so that once it rotated by double the angle, we would get an output at 45 degrees that would meet our needs. This is the 4 segment mask that we created to be able to get 2 beams, the 4 and the 8 segment, so that we could be able to get 2 kinds of the higher order modes. We would generate them with both samples to compare which one was better and whether it improved with the 8 segment mask. Then we aligned the mask and we realized it was possible to do that work. The next part was to produce the beams. The production of the beams went in this kind of way. We made use of like the following setup, and then we placed the sample right there between the linear polarizer and the half-wave plate. I changed the diagrams last minute. As you can see here, the sample is that one that has the bigger mount. Oh, okay. I'm sorry. Yes, it had the bigger mount. So we did that and we rotated the beam through the different segments. So this is generally what we were attempting to do in this point. We were using a Gaussian beam, which was the linearly polarized beam. We radiated it on the polarization mask. It yielded the higher order modes. After it yielded the higher order modes, the next step was to spatially filter the beams so that we can get rid of any diffraction properties where the segments met. After doing that, we were able to get an output beam, which was still a higher order mode, but then it was cleaner. It was clear and it was very clean, so that was very good. This is the, I guess I can't find it. This one? Okay. This is the linearly polarized beam we used initially to generate the beams. I did a graph to be able to prove that it was a Gaussian, and here we did the fitting with the Gaussian. The Gaussian profile, although we also did the void, but the Gaussian is what we're trying to prove that it was a linearly polarized Gaussian profile. The next step was here is where we radiated the masks before spatial filtering, so you could see the diffraction, how it was caused by the various elements. And for the 4 segment and for the 8, these are the outputs we got from the 4 segment mask. You can see that the outputs are pretty good, but when you come to these points here, some of the symmetry was kind of off. Like it was still radially polarized, but we had an off output at these points. Therefore, that led to the 8 segment mask. And as you can note from even just looking at the images, there was a better symmetry, especially at the corners when we increased the number of segments. Therefore, the beam quality, even visually, we could ascertain that it was somewhat better. The next step was to now compare. Here is where we're comparing the radial for both the 4 and the 8. As you can see here, this, I'm sorry. Okay. Yes, so we were able to ascertain that the symmetry at the corners was greatly improved. In these cases, you can see the symmetry at especially the corners, it was kind of better, but diffraction led to a lot of losses, unfortunately. This was for the azimuthally polarized beam. We can see the output for both the 4 and the 8 segment masks. The data was improved. These are some of the results from different publications, which I used to be able to just show people we expected results that looked somewhat like that. Well, this is the graph for the output. It's not very smooth because it was raw data collected from the lab, but we did a fitting with two Gaussians, with a Gaussian modius, and then we realized that the higher order modes generated were easily described as a coherent superposition of two orthogonally polarized Gauss-Hermite modes in the first order. So it yielded the correct results. Well, this point was where we had the dark line. The intensity was greatly reduced at that point. The next step was to test the Stokes parameters. We did this using the rotating quarter wave plate technique. The technique made use of a quarter wave plate and a linear polarizer. It was developed in 2007. There's a paper Schaefer et al. This is the setup we made use of. Therefore, in this case, these were the parts we added, the quarter wave plate and the linear polarizer, where this would allow us to be able to rotate them to be able to collect the data. And the data collected was the power by the power meter, which is the detector in this case. And once we did this over 8 different iterations while rotating the quarter wave plate by 22.5 degree increments, we were able to get the Stokes parameters. This is the setup. The Stokes parameters, this is for first the linearly polarized beam, which we determined was linearly polarized, but it was in the diagonal direction. This is the ideal values. This is what we got. Then we were able to do for the 4 and the 8 segment, and you can see the values are pretty close to the ideal. The ideal parameters are here. These are my results. Therefore, the findings were the correct alignment of the cellophane samples upon cutting would actually allow us to generate the beams of order number +1. Therefore, we're able to generate the higher order modes, and the increase in the number of segments would actually increase the quality of the beam. The losses, however, would be in the way of power of the beam, as we would find that the power would be reduced more by the 8-segment mask owing to the increased diffraction. These are my references. Thank you. Questions?
Can you say something about you mentioned there was some damage by using blue light?
Yes, the first sample wasn't working well with the blue light, but we found another one, but the results, I'm still assessing them right now.
What was the power of the blue light?
The power, we had the laser was operating at around 96 milliwatts initially, and then I made use of the initial part of the setup where I would vary the power so that I would ensure that there would be no damage to the cellophane. Let's go back to that. Now you see in this setup right here, the half-wave plate and the polarizing beam splitter, the first two before the spatial filtering, these are here so that I can be able to reduce or increase the intensity reaching my mask, yes, or the cellophane sample, so that I won't denature the bioplastic material. Yes.
Thank you.
Thank you for the nice talk. I have a question. You have a range of different widths of the cellophane, and you search for one that provides you a half-wave plate. Is it also possible to find one that provides you for a quarter-wave plate, or is it too thick for that?
It's actually very viable and possible. We are working on it. Yes, it's still a work in progress, but for this we were making use of cellophane at 21 milliwatts. It was the one that had the best optical properties. Yes.
Thank you.
Yeah, thank you. I did not, maybe it went too quick. How did you stabilize the cellophane? Did you put it on a glass?
Oh.
Or was it free?
Yes, in the initial states, okay, you're asking in generating the higher order modes. Okay. This is what we did. I made use of 2 glass slides whereby I placed one at the bottom. Then I aligned the segments, and then I placed a second on the top, and I fixed it. Yes.
Did you have any problem with multiple reflection from inside, because there are probably small air gaps? Or?
Yes. At some point, we had a problem with the back reflection due to the segments of glass. What I did at that point, because it was yielding interference patterns, was to decollimate the beam a bit more, so that when it was not as collimated, the reflections would not head back in the same path as the one it would be sent forward in.
Thank you.
No, okay. Okay, no more questions, I hope. Thank you. Yes, thank you.
So our next presenter is Kimoni. Welcome.
Okay, good morning. This work done as an extension of the previous presenter, and so numerical analysis of optical properties of multilayer graphene illuminated by a wide band spectrum of polarized light. The material being graphene to be used in the optical application of how does graphene interact with the polarized light. First of all, graphene is a carbon allotrope. A degenerate of graphite. A single layer of graphite leads to the graphene. How these carbon atoms are bonded in the graphene structure also dictates the mechanical properties of the graphene and also the optical properties. The sigma bonds are responsible for the mechanical properties of the graphene, while the pi orioles, the pi bonds are responsible for the electronic ends, the optical properties. So how this material interacts with these polarized lights, that's our interest. And some previous work has been done on how graphene interacts with the polarized light. And for example, the first work here was done whereby we have different incident angles. But now there are limitations. For example, when we talk of data storage whereby we are interested with much of normal incidence, you find that there are limitations to this work. Other work has also been done whereby the graphene is sandwiched between a grating. The aspect of absorption here is enhanced by the grating or the surface plasmons. So the limitation of this is that the transmittance is limited. So we have the work we need to achieve and see how graphene interact with the polarized light has been achieved by simulation, and we have used the finite element method, which is supported by the COMSOL multiphysics software. And these are the procedures in which we achieved our work. The first part was the parameters and the variables in which the environment is defined, the geometry or the structure of the graphene, and the supporting structure like the substrate, the materials, which is the graphene, and to be as realistic as possible, we have here graphene and then a glass substrate, and then the physics of the material is defined whereby you define the physics of the material as per the refractive index or other physical phenomena. Then we have the boundary conditions which define the environment in which the light shall be incident. Then we have the meshing, computational, and then the post-processing solutions. Then some of the parameters we use for this work is that we used room temperatures, which is 300 Kelvin, and for the Fermi energies, we chose a value between 1 and 7 electron volts, which would be varied by either changing the bias voltage or the doping. So for practicality, the chemical doping of the graphene or changing the bias voltage would achieve the change of the Fermi energy. Then we have the relaxation time, and the wavelength range here is from 200 nanometers to 1700 nanometers, which covers 3 ranges. We have the infrared, the visible, and the UV. So this table, or else the figure 5, shows how the incident, or else how the beam incident to the structure or the geometry. We have beam from the side where we have hair to the graphene, then to the glass substrate. So the light is normally incident to the graphene through the hair, and the light is transmitted all the way to the glass substrate. And the governing equations which define the work are the interband and intraband conductivities of the graphene, and also the relative permittivity, which defines the optical properties of the graphene in this case. So, with linear polarization and several layers, when we have different Fermi energies, we look at how graphene absorbs light at different wavelengths. For example, here we have, in the first graph, we have 1 electron volt. At 1 electron volt in the range of 200 nanometers to 1700 nanometers, we find that a single layer absorbs less light as compared to 4 layers. But there is a phenomenon happening here at the point whereby we have a drop in this absorption. This is a point whereby the graphene absorption properties are governed by the intraband, and they are transiting into interband transitions. So that is when we have this property. So as we are changing the Fermi energy, we can observe some of the properties, like at what point do we have these interband and intraband transitions, and at what wavelength. So that when we have application in data storage, we know how does the graphene behave under linearly polarized light at this wavelength. For example, here we have 200, from 200 nanometers to 1700 nanometers at 2 electron volts. At the point whereby we have the interband transition, or the Pauli exclusion point, it is between 200 nanometers and 400 nanometers. So that point drops as you increase the Fermi energy. At larger or else at higher Fermi energies, this is 4 electron volts, you find that all these transitions are governed by the intraband transitions. So we know at 200 nanometers to 1700 nanometers, the 4 layers have the highest absorption. But at this point, all that transitions are intraband transitions. So the same is also observed when we have as many layers as possible. This for the case of 10 layers. The more the layers, the more the absorption. And this is at a single Fermi energy, which is 1 electron volt. So this shows the points whereby we have the transitions or the absorption characteristics changing is at the point whereby the interband transitions are also changing, which is 600 nanometers and 800 nanometers range for 1 electron volt. So for different Fermi energies, we have the points whereby the interband and the intraband transition change. So this is the absorption properties for the 10 graphene layers. Then this is for 1 layer, the absorption, transmittance, and absorbance compared in a single graph. That shows that between 200 nanometers and 600 nanometers, we have a very high absorbance as compared to the other wavelengths. So at lower Fermi energies, we have a higher absorption at the shorter range. Or else, the interband transitions controls much of the shorter wavelengths as opposed to the intraband, which controls the longer wavelengths. Then we have the reflectance reflects the same phenomenon, whereby as we increase the Fermi energy, the point of intraband transitions moves to the shorter wavelengths until when we have a high Fermi energy, like 4 electron volts, we have all the transitions controlled by the intraband transitions. So whatever was seen in the absorption is also replicated in the reflectance and also in the transmittance. We have a very high transmittance for a single layer, and as you increase the number of layers, the transmittance is low, and that is for every Fermi energy, there is a distinct absorption characteristics and transmittance and reflectance characteristics. And this is for linear polarization. When we have circular polarization, we see resonance points, or the points at which we have a character of absorption being enhanced, or at a point whereby the absorption is quite low. So for example, at longer wavelengths, that is between 800 nanometers to 1700 nanometers, we find that there are points whereby the absorption is close to zero, or for every Fermi energy. So distinctively, the graphene structure absorbs different polarizations at different levels and different ways. And that is replicated for either transmittance, reflectance, and absorption for the different Fermi energies. So in conclusion, we can say that graphene can be used to absorb a different polarization at different levels when you change the Fermi energy, which can be changed by the bias voltage or chemical doping. So we can have absorption of polarized light in the range, or else in a wider range, from the infrared visible range and the UV range, by the graphene structure. The more the layers, the more the absorption. The greater the Fermi energy, the greater the absorption. So thank you. That is the much work which was done, and in recognition of Professor and Dr. Whitty in conjunction to that work. Thank you.
Questions?
Are you planning to do experiments to show this?
Sorry? It's a simulation. It's a
Yeah,
simulation.
but are you planning to do experiments too?
Currently, the work which is done experimentally is only for one wavelength, which is 632, but it's an extension, more work for this one. But it's recommended that we can do more work on it experimentally. Yeah.
So our next speaker is Christabel. So Koki can come first, eh? Yeah.
Okay. Alafu next.
Forward, backward.
So good morning, everyone. My name is Dorothy Koki, and my title is Line Profile Analysis of the 6p state in rubidium 85 for the double and triple resonance spectroscopy. So most atoms we have the fine and hyperfine structures. The fine structures are as a result of the splitting of the orbital angular momentum L and the spin angular momentum S. Now these fine structures are further split to hyperfine structures due to the coupling of the total electron orbital angular momentum J and the total nucleus angular momentum I. Now the spacings in between the hyperfine levels are the hyperfine intervals, and for precise measurement to be done, these hyperfine levels have to be well resolved, and also their line profile has to be generated. Several techniques have been used in order to generate the line profile, such as the saturated absorption spectroscopy and saturated fluorescence spectroscopy. But in these techniques, the drawback is that they have crossovers that are formed. Now these crossovers, what they do is that they merge with the real peaks, hence making it impossible to resolve the peaks. However, double resonance has been used in order to, because it does not have the crossovers. And here, in double resonance, we have the probe, the weak probe, and the strong pump. They are co-propagating. The probe is locked at a cycling transition, and its absorption is monitored. While on the other hand, the 6p state is scanning across, the blue pump is scanning across the 6p state. Now, the 6p state is an open transition. What is an open transition? An open transition is that when an atom is excited from the lower ground to a higher ground, it can decay directly via the dotted blue or indirectly via the dashed red lines. Now, what this causes is that atoms are lost in the lower ground level that is not coupled by any laser. That causes a dark state. Hence, they are not available for recycling. Now, spectroscopy is measurement, and in order to do measurement, you have to generate the line profile. You have to generate the line profile. Now, rubidium has very closely spaced hyperfine intervals. Therefore, double resonance does not resolve these peaks very well. Hence, we propose triple resonance spectroscopy in order to reduce the line width to range to about 2 to 4 megahertz, for which is close to the near natural line width of the 6p 3/2. Now, the first step we did is to analyze the effect of optical pumping on the line profile. The effect of optical pumping on the line profile, where we had first the governing equations, and then we compared the line profile that we generated. Now, these theoretical simulations were done using the density matrix formalism in order to generate the line profile of the 6p state. How was this generated? First, we derived the Hamiltonian of the system. Secondly, we formulated the equations of motions. And thirdly, we were able to determine the line width. We were able to extract the line width using the Lorentzian curve. Now, this is the Hamiltonian that we were able to determine. And this Hamiltonian, we used it in the master equations in order to formulate the equations of motions. These were the equations of motions that were formulated. However, these are not all. The rest can be obtained using the complex conjugate and the law of conservation of population. Now, we compared the line width of the V closed and V open. Now, since the 6p state is an open state, therefore, we assumed that, the first assumption was that the state 1, 2, and 3 are closed, is a closed transition, so that we are able to determine what is the effect of the atoms that are lost in the lower ground state level. Hence, now the second part we had the open V system, which was part 1, 2, state 1, 2, 3, and 4. Now, since state 1 is a shared transition, and the same time, we have state 1 and 2, and state 1 and 3 being driven simultaneously. Therefore, we induce coherence between state 2 and 3. This coherence is the source of electromagnetically induced transparency, therefore forming a dip on the line spectrum, on the line at the center of the line spectrum. Now, these are the spectrum that we got. In the upper ground state level, we had the peaks. The green peak is for the closed V system, and the red peak is for the open V system. Now, we can see that the AIT in the closed V system is enhanced by optical pumping of population, which are the atoms that were lost in the lower ground state level, in the dark state. So this causes the line width to the broadening. This causes the broadening of the line profile. We also compared this, what we got, to the experimental data, which is the red dashed line, and we could see that they do not really compare. Now, we also did the same for the lower ground state level, and the green spectrum was smaller compared to the red spectrum, that is the open V system, and we could see that the optical pumping enhanced transparency. Therefore, the line width also increased. Now, comparing this to the experimental data, they also did not compare. Now, that begs the question, what could be the reason? Then we realized that there was the intermediate states that we did not include. So when we included the intermediate state, each intermediate state has a lifetime. And this lifetime, when atoms are in this lifetime, they act as a temporary delay. So therefore, atoms are not available for re-excitation immediately, hence causing further broadening of the spectrum, which now we found on the blue spectrum that we determined here. So we compared this blue spectrum to now the experimental spectrum, and we also realized that they compared. We were able to compare with the experimental data. That is for the upper ground level. And for the lower ground level, we also noticed that they were comparing. Now, it is also important here to note that the experimental data here used, the double resonance that was used in the experimental data was for enhanced absorption. Therefore, a peak is formed. And in our case, we had double resonance, the V-type system. Therefore, a dip is formed. Now, the only difference between the two is they are an inverse of the other. Otherwise, the line profile is the same. Now, we were able to see that they compared, except for the hump that was formed here, and this hump was due to the intensity of the laser. The probe intensity of the laser that we used was less compared to the experimental data. Now, in order to determine the line width, each peak was generated individually, and therefore combined to get the, each peak was generated individually in order to determine the line width, and therefore also combined together. Now, the line width was extracted at full width, half maximum, and these are the line width that we were able to determine. Now, generally, the cascading V system showed that the line width of the line profiles of the peaks were generally larger compared to the other line widths. Now, are we able to determine that it is true that the intermediate states are the ones that are affecting the line width? Now, what we did is that what will happen if we increased the lifetime by a factor of 10 or a factor of 100? So that is what we did. And when we increased the lifetime of this intermediate state, we were able to see that by a factor of 10, that is the red trace, the line width broadened. And if we increase the line width by a factor of the lifetime by a factor of 100, the line broadening increased further. Therefore, the line width that we were able to determine was for the upper ground level, we got 27. For the factor of 10, we got 29.4. And for the factor of 100, we got 41. This basically means that if we increase the lifetime, what happens? The line width also increases. That is, the spectrum broadens. Now, our solution to this is the N-type system, where we included another laser, and this laser was locked at resonance, and the function of this laser was to repump the atoms that were lost in the lower ground state level, that is the dark state, back to the system. And what happened when we compared? So when we compared with the cascade V system, we could be able to see in the green spectrum that the peaks were visible and not merged together. And that is our end goal. That is what we wanted to see. We wanted to resolve these peaks individually so that we are able to measure, and carry out precise measurements. We also these were the line width that were determined, and we could see that the N-type, in the line width of the N-type, it was less than the line width of the cascading V system. Also, it compared to the experimental results that were used using the velocity-induced population oscillation. But what is important to note here is that in the experimental results, there was a broad background that was removed. And in our case, the broad background was not removed. Now, what is this effect of the broad background? In the experimental results, the broad background for the experimental, when the broad background, which is the red one, when the broad background was removed, the peaks appeared larger and were even better, well resolved. That proves that in our case, when we have the broad background, we are still able to see the peaks. Therefore, if we remove the broad background that is in our spectrum, then we'll get even finer and larger spectrums, peaks. Now, we also compared the N-type system. We simulated the V system now with the VIPO, just to see when it has the broad background, what is the effect. We could be able to see some peaks that were formed, but if we compared with the N-type system, we saw that the peaks were well resolved and larger. Therefore, in our N-type system, we had, comparing with the VIPO, still our line widths were smaller compared with the VIPO, and that was our work. Finally, we were able to reduce the line width of the 6p3/2 using the triple resonance spectroscopy, and this work was done in conjunction with Professor Kihara and Dr. Ogaru. Those are my references. Thank you.
So questions or comments to Koki? Okay.
Thank you very much for nice talk. You mentioned you increased the lifetime. Is that correct?
Yes.
And I'm wondering, how do you do that? Is it only in simulation, or you do that in the experiment by decreasing the temperature?
Simulations.
Only in the simulation?
Yes. Okay, thank you.
Yeah, thank you. So the experiment you did in the vapor cell?
It was a simulation.
Oh, this was all simulation?
Yes.
Ah,
yes.
okay. Are you planning experiment?
Yeah, if I get the equipment.
Yeah.
Yes.
So, but the simulation was about atoms ensemble in the vapor cell, right?
No, it was one atom. We simulated with one atom.
But you.
The Schrödinger.
What did you assume about the motional state of the atom? Did you assume a thermal velocity. So, so basically what I was wondering, in your simulation, did you account for Doppler broadening?
Sorry?
There's broadening with respect to the motion of the atoms in a gas cell.
Yeah.
And in a simulation, you can take this into account.
Yeah.
And this gives you a broader line.
Yes.
And so normally, I think you use double resonance to get rid of this thermal broadening. So in your simulation, you included the Maxwell-Boltzmann distribution of velocities of the single atom?
Yeah.
Okay.
Yeah.
Any more question or comment? Okay, so a clap for Koki. So our next. So our next presenter is Christabel Isangi. Welcome.
Probably one or two words about Christabel. She is doing the experimental work. Part of what Sylvester presented, the simulation work. And she actually arrived this morning. She had gone to the US to attend the CREO conference. So I believe it is well with you, not so much jet lag. Yeah. So that is part of the work that Sylvester is doing. Thank you.
Good morning. My name is Christabel Isagi, and today I'll be taking us through an exploration of the polarization-dependent optical response of a single-layer graphene under controlled illumination. This work is presented by my colleague Sylvester, who is doing a simulation of the same work that I'm also doing here. So. It's not moving. Oh, okay, it's not moving. Okay. Now, what is graphene? Graphene is an allotrope of carbon. It is a single layer allotrope of carbon that is formed or that is made up in a hexagonal lattice. And this material is remarkable because it has been recently discovered, as recent as in 2010. And it is well explored due to some of its superior electronic, optical, thermal, and physical properties. And some of the optical properties that make it interesting for us to dive into its properties such as the optical transparency, the strong light interaction matter, the superior polarization-dependent optical properties also are some of the remarkable properties that make it interesting or that informed our study that made us dive into this particular material. As we can see now, a single-layer graphene made up of allotrope of carbon is as shown in our diagram here, where we have a structure of a graphene sheet. Because in this study, we are looking at a single layer of graphene that is produced by chemical vapor deposition, that is the CVD method, and it is etched onto a glass substrate. Now, our study today, we are going to look at this optical response, which are influenced by, properties or factors such as the substrate that is in use, the doping level, and also the incident light polarization. So some of the polarization that we delved into in this particular study are polarization such as linear, circular polarization, azimuthal, and finally the radial polarization. Now, when we look at Zhang et al. 2020, they looked at, they did a review of the polarization of optical devices that are based on graphene materials. And from this, they found out that this polarization dependence, these effects and broadband absorption enhancements of graphene, can be done under total internal reflection. And this work was important when it comes to informing our study, because from this we learned that polarization characteristics of light, can be used to indirectly measure some of these changes of our material here. Also, looking at Wang et al. 2021, delved into the graphene plasmon polaritons, which are characterized by high carrier mobility, strong localization, and also low consumption and high tunability. What are plasmons? Graphene's plasmon, these are the surface excitation or the electronic excitation in graphene, which are responsible for some of these electronic and also optical properties. Now, in our study, before commencement of our experimental study, we had to come up with the right parameters for our components while doing the laboratory work. And now we delve first into the lens pinhole spatial filtering process, which is a process of cleaning or making sure that the beam is of the right parameter, is cleaned, is collimated before commencement of the experiment. And now, when we followed the mathematics here, we saw that the pinhole that we had to choose, its diameter had to be that of 30 micrometer, and we did that, and we were able now to do our lens spatial filtering process, whereby it was placing the microscope objective and the pinhole on the path of the beam. Now, our beam that we were using was the 632 helium neon laser. That is what we use as our laser source. And from the laser source, through this process, we were able to now conduct experimentally our lens spatial filtering process. From there, we went to our first objective, which we were supposed to generate linearly polarized beam. Now, this after spatial filtering, we were able to do this by using a combination of a half-wave plate and a polarization beam splitter. The function of each of these components was vital when it came to the generation of linear polarization, because we needed to generate this particular polarization and use this polarization on our sample, just so as to determine, what are the optical response of our material when subjected to this particular polarization. Now, with PBS or polarization beam splitter, we were able to split our beam into two orthogonal components. That is the reference beam and the transmitted beam. And it is the transmitted beam that went on ahead to interact with our sample, and from there we were able now to infer our results. This is the schematic setup, and experimentally this is how all the components were arranged. From there, we went further on to now generate our second type of polarization, which was the circular polarization. And from linear polarization, we just had to introduce two more components that enable us to finally be able to generate circular polarization. And this was, we introduced a half-wave plate onto the path of the beam, and a quarter-wave plate that was oriented at an angle of 45 degrees. Now, the half-wave plate introduced just after the reference beam that comes from, is transmitted from the PBS, its function was to introduce both components, that is the horizontal and vertical components of light, which when now oriented at an angle of 45 degrees, results into a generation of circularly polarized beam. This is the schematic setup, and experimentally, this is how our components were arranged. And from there, we had now to sit down and ask ourselves, we've been able to generate circular polarized beam, but we cannot see. It is something that cannot be seen. And so it was vital now for us to do what is known as testing for circular polarization. And this we did by introducing a second quarter wave plate onto the path of the beam and a linear polarizer. And when the first axis of the quarter wave plate and the transmission axis of the linear polarizer were aligned as per the beam, we were able to see traces or changes in intensity when we observe on our parameter, and this was a clear indication or an indication that our beam truly has been converted from linear polarization to circular polarization. From there, we now went on to our last two types of polarization, which was the azimuthal and radial. And as my colleague Sandra has looked at it, the generation of azimuthal and radial polarization was done by use of a cellophane sheet that was cut into 8 segments. And from there, we can see our beam really passed through a lot of spatial filtering through all those components. And at the end of it all, when we observe on our CCD camera, we were able to see now the donuts that when changed from one polarization, that is from the azimuthal to radial polarization, the beam form now we were able to use it to conduct our tests onto our sample. Now, what was the point of doing all this? We did the experiments so that to be able to, use Fresnel equation formalism at normal incidence and be able to come up and look at evaluate the coefficients, that is the amplitude coefficient of the reflection, absorption, and transmission. Now, during experimentation of our work, we looked at three samples. That is, we had the graphene that was etched onto a glass substrate. We also had an FTO, which was our secondary sample, and finally we had a glass sample. Using Fresnel equation formalism at normal incidence, we were able to evaluate the transmission amplitude coefficient, reflection, and absorption over 3 samples at normal incidence, and these were the values that we were finding. And these coefficients, they were important because they informed our optical properties that we were looking at. That is the transmittance, reflectance, and absorbance. And these were the values that we were finding, which agrees with theoretical values that have been done with other authors. And these values also, they translate or are important when it comes to applications that are going to be based on graphene. Finally, we were also able to do for circular polarization, and we were able to find similar results. And from there, we used our results now to graphically represent our data or results that we were finding. And this is the case of linear polarization, whereby, as I'd said earlier, our beam was split into 2 orthogonal components. And just by using the 2 components, we were able to graphically represent the data of our incident beam and transmitted beam and see what is the relationship between the 2 sets of beam. And as you can see, is that we were able to now just come up with a linear relationship between the 2, showing that as our transmitted beam was increasing, so did our incident beam across the sample, meaning our sample is suitable or is sufficient enough in application where high transmission of light is required. Like we can have the windows, the smart windows, they can use graphene, because with graphene we can have controlled temperatures or controlled light coming in and out in our given setup. Now this was the results that we found for the case of linear polarization. We were able to also find a similar trend when it came to circular polarization, and also for the case of azimuthal and radial, we used a line of fit to show that it really does follow a similar trend with a gradient of 1 for the two type of polarization. Another important thing that was worth us investigating was what happens when we vary angle of incidence. Sorry. Now my slide is not moving. Yes. what happens when we vary angle of incidence for the different types of polarization? Now, for the case of linear polarization, this is the relationship that we were getting when we vary angle of incidence and record the resultant reflectance and transmittance onto our sample. And as you can see in our graph, is that the two type of optical properties in our sample, they form a similar trend. That is, as one aspect or as one optical property was increasing, gradually increasing, the other one was also gradually decreasing, meaning when it comes to the two types of optical response in our material and its application, there is need for one to be evaluated based on the need. Like if we need an application that requires a higher transmittance, now it means that in the same application, we have to factor in reflectance of our material. Now, when we look at circular polarization, we see that clearly this showed a clear change or response when for our reflectance and transmittance, whereby an increase in reflectance resulted to a resultant decrease in transmittance. And this trend here proved that our material truly, when it comes to its application and when using circular polarization, there is going to be a clear relationship between the two optical response. So in our discussion and conclusion is that as we've seen in our different graphs, is that for the case of linear polarization, varying it with respect to transmittance and incident beam, is that the graphs were forming a linear relationship, or the graphs were linear, with a higher transmittance being observed for each type of polarization, which is efficient when it comes to application that requires a higher transmittance of light. These are my references. Thank you.
So questions or comments?
Yes, very nice results. When you do this data as a function of the angle, the two should add to one except for the absorption, right?
Yeah.
Plus the absorption.
Yes, yes.
But do you see a difference? Because from the graph I cannot see. If you add point per point, how does it fluctuate?
When we this one.
Yeah.
Okay. First of all, it is a normalized curve of reflectance and transmittance, and from conservation of energy, when you're supposed to look at the reflectance transmittance together with absorbance, the total of it all should add to 1.
Yeah.
Yes. What is the question?
But does it add? Because it doesn't look like dilute. Or is just you have to take into account the absorption here?
Yeah, here we had one, what is it called? We had one assumption, that is that our sample was 100%, or it was transmitting more than it was absorbing and reflecting. And so when it comes to conservation of energy, we were able to just say that from the summation of the two, they added to 1. Summation of the reflectance and transmittance added to 1. Yes, because with our material, it is a monolayer of graphene. It's very thin, and with that, we were able to assume that absorption was infinitesimally small. Yes, so we did not put that into account. Yeah.
Okay, thank you.
Some more questions?
I think the point is, according to what she's asking, I think the two curves, you should be able to show that the two are going to add up to one.
Okay.
I think that's probably something you need to do.
Okay.
Of course, that was a point of discussion as a point.
Yeah, okay.
Okay. A clap for Christabel.
That is part of the work that we are doing at the National Institute for Optics and Lasers. We still have some more experiments, and two of which are going to be covered next week. We have Dr. Joroge is going to talk about art of second generation. He was quite interested from what Hania was presenting. So part of his presentation is going to talk about what we are doing in that area. We are also developing a platform which is going to be used as a point of care, at the point of care for the early detection of malaria infection. So that is going to be also covered by Dr. Kenywa next week, who has been spearheading that work. So next week we are going to hear more about that area of research as well. The work that has been presented is ongoing. This work began about a year ago. And in some cases, like what Koki has presented, we are still procuring the equipment so that we can be able to experimentally determine the narrowing of the lines. We have two lasers, a 780 and 420. They are tunable. So those we have, but we are also in the process of acquiring more components, and we shall be able to do that work experimentally as well. Thank you so much for paying attention.
So thank you, Professor Rurimo, for that wonderful overview of what we are doing at the National Institute of Optics and Lasers. Our next presenter is Mujida. Our topic will be assessing of second order correlation function of quantum states from its Wiener functions. Okay, a small correction. She will talk about the squeezing light via self-induced transparency of solitons. So let's clap for her.
Okay. Excellent. Okay. Hi everyone. So I had one lecture on Monday where basically we covered the basic for the quantum state, current state, squeeze state. And today I would like to talk about something slightly different, but also related to the material that we covered on Monday, and also some of them are related to what Nikolai also talked about. But this is purely theoretical and simulation work. So at the moment, I'm not talking about any experiment. So the topic is quantum squeezing via self-induced transparency in the photonic crystal fiber. So let's start with the Joel Russell. So I think he was engineer, and he was somehow was doing some maintaining work into the channel, and he observed, what he observed was quite interesting. He was observing a mass of water moving all around the channel without the shape of water changes. Later, he back home and he tried to reproduce that in a tank. He wrote about it, but at that time he did not call that as a soliton. He found that very fascinating phenomena. But these soliton waves are not, so here, for example, you see two soliton waves into the water, they are colliding to each other. But they are not only observed into the water waves, they can be observed in acoustic waves, they could be observed in cold atoms, they could be observed in optics as well. So the first, later there was some theoretical work that they have basically tried to reproduce that in theory. Then they called these sorts of waves as a soliton. The first theory work about the prediction of the soliton in the optical fiber was basically in 1973. And then 10 years after, they observed that for the first time into the optical fiber. Then there was more work regarding to the applications and things like this. Oh, this is very tiny. Okay, all right. But what we're going to talk about is this soliton basically due to the self-induced transparency. So before I move to the actual topic, I would like to start from the atom field interaction. So we have a field interacting with two-level atoms. Atoms at the moment are at first located in the ground state. What the field does is to bring them up to the basically excited state. So if you look at the Planck sphere at that time, it's pointing down, and then when it comes to the excited state, the Planck sphere goes to up. So in this case, when you have a pulse interacting with atoms, we can define very important property, so-called Rabi frequency, which is basically a multiplication of the dipole moment by the field. What we can define is a quantity so-called area of the pulse. And area of the pulse is integral of the Rabi frequency over the pulse time. So this can basically tell us about the behavior of the atom when the pulse is interacting with them. For example, if we have a pi pulse, what will happen? Field interact with two-level atom, bring it to the excited state, and leave it as it is. So if you look at the population inversion vector over the time, you see from the ground state, it goes to the excited state and just leave it there. So it's such a pulse that does this to the atoms, called pi pulse, because it has area of the pi. So if to integrate over the Rabi frequency, you will get exactly pi. How about 2-pi pulse? 2-pi pulse brings atom to the excited state and then brings them down also to the ground state. So you can see that here into the population inversion. It goes to the excited state, and after it leaves the atom, it brings them down to the ground state. Again, integral of the Rabi frequency for these pulse will be 2 pi if you do that. How about 3 pi pulse? 3 pi pulse, excite the atom, bring them down to the ground state, excite them again, but they leave them in the excited state. So let's look at the propagation of these pulses into the medium. If integral of the pulse is pi over 2, what will happen when it propagates into the medium? At the first step, it excites the atom and leaves them excited. So when you look at the Rabi frequency, the pulse is has its shape. But after it propagates into the medium, you see it started to decline. And if you look at the population inversion, they see a small excitation, but not really. And then after a little bit of the propagation, there will be no excitation, and pulse will goes away eventually and get absorbed by the medium. But a 2 pi pulse, which is basically a soliton pulse, after interacting with the medium, because it excites the atom and brings them down again to the ground state, so it doesn't lose anything. So it continues to propagate into the medium. A 2.5 pi pulse, it excites atom, brings them down to the ground state, leave them in the superposition of the excited state and ground state, and when it propagates into the medium, that pulse starts to reshape. So it starts to reshape, and the area of the pulse starts to change until it gets stable onto a soliton pulse. So if the area of a pulse is larger than 2 pi pulse, it shrinks until it reaches to its soliton power. However, if the area of a pulse is larger than 3.5 pulse, so basically we have 2 excitation into the system. So this pulse has area of 3.5 pulse. It excites the atom, bring them down to the ground state, excite them again, but do not bring them completely down to the ground state, leave them in the superposition of the state. And during the propagation, the pulse basically intensify until it reaches to 2 solitons. So at the end, if I leave that and continue, it will shape into a pulse with an area of 4 pi. And when it becomes a 4 pi, then it starts to split in 2 soliton pulses with the power, which each of them has the area of 2 pi. So this goes into the area theorem, so the propagation of the pulse. So you can see that from here. If the area is below pi pulse, it will get absorbed. Above pi, between 2 pi, reaches to the 2 pi, which is the soliton power. Above 2 pi, below 3 pi, shrinks to the 2 pi. Above 3 pi, below 4 pi, above 3 pi reaches to 4 pi, and above, below 4 pi shrinks to the 4 pi, and so on. So basically, what we need for the self-induced transparency are 2 ingredients. We need a gas to be in the resonance, and we have a pulse to be in the resonance. These 2 are interacting with each other. Now, if the power of pulse is high enough and the time duration of the pulse is less than lifetime of the atoms, what will happen is that the front part of the pulse put the atom into the superposition of the excited state and ground state, Then it comes to high peak of the pulse. It brings them exactly to the ground state. But because pulse is shorter than lifetime of the atom, when it leaves the atom, it brings them down to the ground state, but it will not be influenced with spontaneous emissions of the atoms. So basically, it leaves the pulse before they emit into the ground state. In this situation, pulse will not get absorbed by the medium. Medium becomes transparent to the pulse, and pulse continues into the medium. In such situation, we say self-induced transparency soliton is generated. However, if the pulse duration is longer than lifetime of the atom, what will happen is before pulse leaves the atom, they will basically emit to the ground state, and then a pulse after a little bit of the propagation becomes absorbed into the medium, and we don't have anything after if you leave the pulse for a few seconds, we will not get any soliton. So in this case, we don't get any self-induced transparency. So in order to get self-induced transparency, we need pulses which has the time duration less than the lifetime of the atoms. So a little bit of theory. Let's start with a simple model. So start with the Hamiltonian of the two-level system, which is interacting with the field. D here is the dipole moment of the atom. And E basically is the electromagnetic field with the polarization vector. How we do look at the dynamic of the system. So for such a perfect system, what we use time-dependent Schrödinger equation. However, this time-dependent Schrödinger equation is whenever everything is perfect, we have a pure system. What we know in the reality, that doesn't work. So our states are usually mixed due to spontaneous emission, damping. Our system are usually considered as an open quantum system. That's where we go to the master equation, and we have to work with the density operator. So in this case, we solved the master equation, which has the name, or von Neumann equation. Okay, before I go further, let's review some basic about the lifetime broadening of the atoms. So atoms basically we can consider three main broadening for the atom, which is natural broadening, which caused only by the spontaneous emission and lifetime of the atoms. Then if we have a collision into the system, there is another type of broadening, so-called pressure broadening. And then if we have if we are working in the room temperature, so we have another type of broadening, so-called Doppler broadening. These are the main broadening that one can work with. Based on that, we can classify the medium as well. So a medium which has Lorentzian broadening, so-called homogeneous medium. And in the homogeneous medium, all the atoms have the same spectrum. And in the medium, which atoms basically have a Gaussian broadening. In this case, we have in homogeneous medium, and atoms are not specifically have basically the same spectrum. So if so a little bit of how you define this Lorentzian broadening, you find that everywhere. So basically, if we have the radiative lifetime of the atoms, we can, or if we have the spontaneous emission rate of the atom, we can get the lifetime easily. And from that, due to the uncertainty principle for the energy, we can calculate the delta omega, and from that we can basically find the spectrum function for the Lorentzian broadening. So the Lorentzian broadening is only dependent on the spontaneous emission rate of the atom or the lifetime of the atoms. And for the collision broadening, basically because of the collision which causes between the atoms, this lifetime start to decrease. So basically, we can define a lifetime so-called collision time. And if we consider the collision into the system, this collision time is less than the lifetime of the atom, and we can basically use this previous equation, but instead of using tau, we use the collision time, and there we can have the line shape for in this case. This is dependent on the pressure and on the temperature of the system. Doppler broadening has this shape, a Gaussian shape, and the width of this related to the temperature into the system. So the room temperature, it becomes very like a Gaussian. So in the work that I'm going to show you, we will only doing working with the lifetime broadening and Doppler broadening. So in this case, when we are in the room temperature, atoms will have a Vaught profile. And this Vaught profile is a convolution between the Gaussian line shape of the atoms and also the Lorentzian line shape of the atoms. Yeah. So there, that was just a review. Now let's look at the what we are looking for. So a soliton also can be explained with a coherent state. Remember, on Monday we reviewed the coherent state. We say coherent state is a result of the displacement operator acting on the vacuum state. In the vacuum state, we have vacuum noise or fluctuation. So the coherent state also has this fluctuation as well. We learned that because this, the quadrature x1 and x2 do not commute with each other, therefore it's not. Therefore, they raise the Heisenberg uncertainty principle, and because they are Hermitian, therefore they are observable. We learned that it's possible that we reduce the noise in one of these quadrature in the expense of increasing that in another one. And, but we also learned this reduction must be below than the vacuum noise. If it's not below the vacuum noise, we cannot call the state as a squeeze state. So, for the squeezing, on Monday we covered parametric down conversion. Today Nikolai talked about the Kerr squeezing, and today I will talk about squeezing caused by the self-induced transparency. So here is the model that we have. We have a system or a hollow core fiber filled by atoms, let's say 2 levels atom at the moment, but we extend it later. We have, we have a coherent field which is interacting with this atom, and this coherent field it also has it's a soliton pulse, so it has area of 2 pi. So remember we mentioned it brings atom to the excited state and brings them down exactly to the coherent state. And both of them are interacting with the reservoir. So we consider interaction of the field with the reservoir, interaction of the atom with the reservoir as well. So three main interaction we have into the system: field and atom with the bath or their own reservoir, and also field with the reservoir as well. So we say open quantum system, what we need to do, we need to write first the master equation. So here is the shape of the master equation that we gonna work with. The first term explain interaction between the field and atoms. The second term explain interaction of the field with the reservoir. And the third term explain the interaction of the atoms with the reservoir. Each of them introduces different type of the noises into the system. For example, when field is interacting with a reservoir or with the fiber, we get it introduces a linear loss into the system. And when the atoms are interacting with the reservoir, we have basically incoherent pumping and dephasing, also longitudinal damping and transfer damping as well. So here a little bit something for a student. Working with a master equation, as soon as you only have a two-level system, should be fine. But the problem comes that sometimes we would like to go for the higher level system, or we would like to increase the number of the atoms. And then the Hilbert space starts to exponentially increase. The same with the density matrix. So the density matrix density also starts to exponentially increase. For example, here you can see the size of the density matrix as a function of the system size. You see it exponentially increases. So therefore, it becomes very hard to do that, to look at the dynamic of the system. So for that, we need another solution. So remember on Monday, we say we either work in Hilbert space or in the phase space. And we say in the Hilbert space, we are working with the operators. In the phase space, we are working with the functions. But because these functions are not, this mapping between Hilbert space and function into the phase space is not unique. So we have different type of the mapping depending on the system that we are looking at. So for the self-induced transparency, in the semi-classical model, it has been very well understood. What is our concern is about quantum models of that. There has been some work using the linearization approach, but that's not the best way to basically simulate the full quantum noise. So the best way would be to really go to the phase space and use the positive P representation to map all the noise into the system. So positive P representation has been basically developed with Peter Drummond in Australia, New Zealand, and I think and Gardiner. And the main advantage of the positive P in compare with Wigner that we talked on Monday is that in Wigner it's possible you get the negative probabilities. So basically it doesn't give you a precise, yeah, really good, thank you. Precise simulation. However, positive P avoid negativity into the system, and also it's possible that you include the higher order interaction term into the system. And because it's based on the normal ordering operator, so if in the experiment they would like to do a kind of amplitude squeezing, amplitude direct detection, then this could be also easier or convenient, I would say, for the direct detection. Excuse me. It seems I can't change it. Okay, thank you. There's one problem with the positive p is that we cannot visualize it like a Wigner function. Here, it's just one example of the Wigner function comparing semi-classical model of the Kerr squeezing and a fully quantum model of the same Hamiltonian, but with the Wigner function. As you see a Gaussian distribution, and you can really look at that and see what is going on. However, for the positive p, you don't get such a plot. You can't visualize it because of it's mostly a computational method rather than has a physical meaning. Could you please go for the next slide? Thank you. Next. Okay. So from the master equation, we can get into the phase space by properly basically define the C numbers. So what we need to define for the positive P is a complex C number depending on the equivalent with the operators that we have into the master equation. This is not that straightforward that I put it into the in this slide. There are some rules that you need to apply, but when you do that correctly, eventually you will get a type of equation which is so-called Fokker-Planck equations. And from Fokker-Planck equation, you can derive E2 equation, which is basically a stochastic equations. And those equations are things that we would like to work with. Please next. So remember the master equation that we had. We are not going to work with that. These are things that these are 4 equations that we got into the phase space. And this is the basics of the simulation. If you really look at that, the first one shows the dynamic of the propagation of the Rabi frequency. The second one, polarization vectors. And the third one, population inversion vector. So if I remove the last part, you know them, they are Maxwell-Bloch equations. So basically, the only new terms in this equation are the last part, which explain the noise into the system. And that's what I really need, and need to be very well explained. Could you go for the next slide? Okay. So what are these noise terms? For the Rabi frequency, the noise terms come from the linear losses into the system and also interaction of the field with its own reservoir. So this is the average NEA is highly dependent on the temperature. So if the temperature is 0, you consider that 0. Therefore, there is no noise term for the Rabi frequency. For the atomic part, for the polarization vector and the population inversion vectors, the noise terms come from different sources. So the first one is related to the interaction of the fields and atoms. The second term related to the dephasing, which is caused by interaction of the atoms with the reservoir. And the third term comes from the in-current pumping. For the population inversion, the same. The first term comes from the longitudinal damping. The second term, interaction of the atoms and field. And the third term comes from the, again, in-current pumping to the system. The eta here, this is important, the eta here is independent Gaussian function. So basically, a random number with the standard deviation of the time step. Oh, that works now. Good. So if we want to look at the some toy model results, let's consider the we have a second hyperbolic pulse, which has the area of the 2 pi pulse, equivalent like a soliton pulse. So the Rabi frequency is basically a second hyperbolic pulse. And atoms are located into their ground state. So this is the initial condition that we have. We would like to look at the first, if people do direct detection into the, in their experiments, so we would like to look at the direct detection first. So in this case, in the theory, we define operator M, which is integral of the Rabi frequency multiplied by its conjugate over the time. So in this case, we need to get the variances from this operator here, normalize it, and see if a squeezing happening into the system or not. In the setup of the experiment, something similar to that should be. So you have a laser here. You load your hollow core fiber with some atoms, depending on what is more convenient for the experiment, in the experiment, and then you get in the output you do the detection. So what we have learned is that if we only work with the soliton power, we will not be able to observe amplitude squeezing in our system. However, when we are slightly above the soliton power and particles start to move into the area, into the medium, then we start to observe amplitude squeezing into the system. Before this, when we are below the soliton power, also we do not observe any squeezing into the system. So we also look at the different effects of different parameters into the system, like damping, and we learned that damping can reduce squeezing about 1 dB in all sorts of the area, all range of the area that we can observe squeezing. Okay. So that was just a toy model. In the experiment that there was some attempt of doing the experiment a few years ago. So basically they were trying to do that with the mercury atoms. And basically in that experiment they could basically load the hollow core fiber with the mercury atoms. There were some attempts of using rubidium, but rubidium had problem because it sticks to the glass, and these hollow core fiber are made of the glass. So therefore they switched to the medium, to the mercury. So let's look at some realistic simulation. Could you please? Thank you. So for the small sample of the mercury, we have all these sort of all of these isotopes. Isotope 202 has the highest abundancy, and only isotope 199 and 201 split into two sublevels. First, let's look at the result for the isotope 202. Then I will show you some of the results where I consider all the isotopes and all the hyperfine structure of the mercury into the simulation, and see what we can learn from that. So if you look at the spectrum of the mercury, there are there is one transition which is interesting for the SIT, and this is transition from 3pi2 to 3d3. So if we consider only this transition, could you please? One back? One, okay. Then. One forward? Sorry. Okay, thank you. And this time I don't want to do amplitude, only direct detection. I also would like to apply homodyne detection as well. So in this case, in the homodyne detection, we have a harmonic oscillator generated from the same laser. And by changing the phase of this harmonic generator, we are looking at a different quadrature and to see basically where the most squeezing is happening. So the operator that I'm working at and I'm interested into its variance will be this operator here, M, which contains the local oscillator. Yeah. So here only I'm showing you the isotope 202 for the mercury. You see optimum squeezing over the phase of the harmonic oscillator. So the majority of the squeezing happening at angle 0. And when I moved, go away from angle 0, it started to decrease. So that means that for SIT, if I gain any squeezing, that will be an amplitude squeezing, which is happening at angle 0. And if I look at the squeezing as a function of the fiber, you see somewhere here, I see the most of the squeezing is happening into the system. So let's now look at the whole sample. So in the sample, we say we have also different isotope, and two of them can also split into the sublevels. If I consider all of these transitions, and all the allowed transition for the isotope 199. Then I move to the room temperature because experiments not going to be done into the low temperature. They do that into the room temperature. Yes, okay, perfect, thank you. Thank you. Yeah, what I learned from that. We are considering all the isotope, all the hyperfine structure, and we move to the room temperature now. What we have learned is that let's consider, it's very hard for me also to read, and I can't remember the numbers also here. A pulse with a certain duration, it must be 1 picosecond, I think, at room temperature and at 0 temperature. If I do the detection of the squeezing, I will see at the room temperature I will not see any squeezing happening. However, when I move to the 0 temperature, I observe the squeezing. What I should do? They would like to do the experiment into the room temperature. So I started to go for a pulsar which has even a bit shorter lifetime. And then what I learned from here is that when I move to the pulse which are more shorter, there I will be able to also see a squeezing at the room temperature as well. So by what I learned from this is that in the case of the SIT, a short pulse helps a lot because then I will not be interrupted with the type of the noises, thermal noises, and all sorts of dephasing that happen into the system, and that will not influence squeezing. So by now, I would like to finish my talk here, and if there is any question, I would be happy if I can answer. Thank you.
Okay, questions or comments?
Okay, thank you so much for that presentation. It was a good one. Now, there's a point you have talking about the passes. You have talked about the passes where the pass is higher than the coherent. Okay.
When I'm talking about the
pass.
bath, reservoir, you mean?
Pass.
Pulse. Pulses. Okay, sure.
I'm sorry.
No, I'm, yeah, I'm sorry.
I would like to know if, for example, the coherent, the pass is higher than the coherent. What will happen? Because you are saying that it will be sightened from the ground state to a sign sentient, then it will go back to the mean room between the sightened and the ground state. What if the pass is lower now than the coherent itself?
If the pulse area is above 2 pi pulse, it will shrink to become a soliton, to reaches in the soliton power. So basically it reduces to becomes 2 pi pulse. And while it's reduced, also it influences the atom excitation as well. So for example, at the first step, it brings atom to the excited state, brings them down, and then brings them to the excited state again and leave them there. But because pulse is doing its reshape, basically it's doing the propagation, reshaping happening for the pulse, for the atoms the same, it's happening. So it reduces, the excitation reduces like the pulse reduction into the area.
The second question is about the experiment, where we have seen that there's a squeezing at the room temperature. What about if the temperature is higher than the room temperature? What would happen?
This is, I mean, temperature is not at all good for the SIT. And the only way that we could get some squeezing at the room temperature was to go for very short pulses. It's highly depend on, I mean, how, on what sort of laser they have, or how short is their pulse and things like this. Otherwise, I would say going for the higher temperature definitely is not good for SIT, so they will not get a squeezing from that.
More questions or comments? So do we have questions on the online platform? Okay. So I think a clap for Mojit.
Thank you.
So today we come to the end of the talks. So now the students will move to the computational lab where you will have a practical session. So thank you for coming. We appreciate. So you can move right away because we are going to have one session before lunch. So the first idea is, I think, we save some time for the afternoon session also.